Okay, let's see how this goes. All right, so you guys have a nice polynomial curve here, right? And what we're going over is that curve sketching guidelines. So the first thing to do, remember, is to determine the what? We need to determine the domain here. Okay? It's a set of all input values. Now, what you may want to consider is, what kind of function is this? This is a what? Oh, it's a polynomial function. And what do you guys know about polynomial functions? What's the domain of polynomial functions? All real numbers. Good. So every real number can be used as an input. Okay. Thank you. I'm sorry, you guys. All right. Let's get this coffee in us. Okay, good. Now we can see. So you got a polynomial function, all real numbers. Okay, so that's the first one you have to find is the domain. What comes next after this? Do you guys remember? What comes next on your curve sketching? Oh my God, we got to determine the what? You're going to determine the intercepts, right? Let's just write this down this way. Okay. So we're going to find those intercepts. Now we had two types again. You have the x-intercept, right? And you have the y-intercept. So you actually have two procedures again, okay? So for the x-intercept, what did you guys do for the x-intercept? Or what do? You guys remember? We say let y be 0, right? The y coordinate's going to be 0. And if we do that, you'll end up with the polynomial. Yes, it'll be 0 equals your polynomial, but I like to put this as x cubed plus 6x squared plus that 9x, and then that equals 0. Is that right? So this is how we find the x-intercept. We use that relationship that you're going to let x be 0 or y be 0, right? And then you solve for x. Okay, so guess what you guys have? You have a nice what? What do we have here? We have a polynomial. So you're going to have to factor. So when you factor this, what comes out? Greatest common factor here, right, is going to be x. What's the quotient? X squared plus 6x plus 9, and then that equals 0. And again, so you guys know, this is that greatest common factor. This is the quotient. What are you supposed to do with the quotient now? Factor. So you're going to get x, x, x. This will equal 0. I think this is x plus 3 and x plus 3. Is that right? So if you can say, or you look at it as x times x plus 3 squared is 0. And by the 0 product rule, I get x is 0. Good. I get x plus 3 squared is 0, which means my x plus 3 has to be 0. And I subtract my 3, I get x equals what? -3. So ladies and gentlemen, these are the locations, these are the locations of my x-intercepts on my curve. So formally, we may want to write this down formally. The x-intercept location is at, go back over here. See how we said this? We said what? Let y be 0, right? Let's put that in red. Let y be 0. What that means is my y coordinate value is always 0. And we need to find the x coordinates, and we just did. What's the first x coordinate? 0. What's the next one? -3. These are these x-intercepts. So here's going through the details here. Now you have to do the same now for the what? For your y-intercepts. But what's the procedure for the y-intercept? You let what now? X be 0. You solve for y. Now the nice thing about this is it's already solved for y. Okay, you guys okay with that? It's already solved for y. So what that means is you got to plug in 0, 0, 0. And what do you guys notice if you plug in zeros there? It's going to be 0. So similarly then, we have a point for this. You let this time you let x be 0, so that's always 0, and you found that y is also 0. So this is the location of your what? Yeah, of the y-intercept now. So I got y-intercept, and I got x-intercepts, okay? So there you guys go. Okay, what comes next? If you guys know about this, there's some symmetry here. Or is there not, right? So if we consider the symmetry idea that we said, the symmetry happens only if the function is, we talk about being even or what? Or odd here. Remember that? And I give you guys the definition of being even, definition of being odd. Now, if I go back here, I think a symmetry, what do you guys know? Is this even? Is it odd? Or is it neither? Because if it's neither, then it's neither. Okay? It doesn't have to be any of these. Okay? It could be even. It could be odd. How do you guys know about symmetry? What do you have to do to find symmetry? Yeah, you got to plug in that minus x. Remember that? Okay, so it's going to be even, odd, or it's going to be neither. Neither, neither. All right. So if my function f is, what was that function? Right? What was the original function? X cubed. Right? X cubed plus what? 6x squared. So here's what we do. Wherever there's an x, replace it with what? Negative x. And you end up with f of minus x being negative x cubed plus 6 times negative x squared plus 9 times negative x. So f of negative x gives you negative x cubed. This is going to be actually what? Yeah, it'll be positive 6x squared, right? And this will be minus what? 9x. Now, even is when these two things are equal to each other, right? Remember, even means that f of minus x is the same as f of x. That's when the function is even. And what do you guys know here? Are they the same functions? Nope, they're not. So let's put a not equal. And that simply means that, that this is what? F is not what? F is not even. Now, how do we find again when the function is odd? If you guys remember. Yeah, what you have to have is this relationship. F of minus x has to be the same as minus f of x. And so we have to consider what minus f of x would be. Change the sign for f of x. So over here, we get minus what? X cubed plus 6x squared plus 9x. What does that give us?
It wouldn't be negative 6x?
No, it's positive. You know why? If I square negative, what's the deal? Positive, yeah. So anyway, let's write this down. This is going to be minus f of x, and that equals, let's find this out. This will be, minus x cubed minus 6x squared minus 9x. Is that right? So far, so good? Okay. So go back here. We have to check f of minus x is what you guys see up here. Is that the same as minus f of x? No, they're not the same. Where's the difference? Right here. This plus and this minus, right? Everything else is exactly the same, but those two signs. So when that happens, that's enough to say what again? That these are not equal, And we can also say that f is what? That's not what? Odd either. So what we know here is there's no symmetry. Okay? What we know is that it's neither even or odd. It's a neither situation. It's also not periodic because it's not what? It's not a trig function. Is that right? Anyway, so we're going through the analysis of a curve, and that's what this course is called, really. If you guys want to think about calculus, you're kind of thinking of it right now. This is it. If you had to summarize this to people that you know, say, what are you doing? I'm doing analysis of a curve in some fundamental way. All these little tools we talked about are really coming into play. Notice this is a nice continuous function, right? We're going to work with that. But we're looking at all these details. So, okay. What comes next? Yep. Asymptotes. Now, I'm going to start with the easy one. All right, they're all easy. What do I mean by asymptotes? First of all, I know there's no what? There's no vertical what? Asymptotes. Okay? How do I know there's no vertical asymptotes here? Huh? Because this is actually what kind of function? This is a polynomial, is that right? Yeah. Polynomials do not have what? Vertical asymptotes. In fact, polynomials are continuous everywhere. This is our beautiful rolling hills curve, a nice continuous curve. It's not a rational function, right? So there's no vertical asymptotes. Good. Okay. So we checked what we call, I'll abbreviate this as what? VA. Now let's check the other one. What's this? Horizontal. Now remember, I just gave you guys, we just worked on the idea. If either, remember this? The limit as x goes to infinity of the function is a finite value L, or that limit as x goes what? To minus infinity of the function is a finite value L, right? Either of those have to be satisfied in order to have a horizontal asymptote, and that happens at y is L, all right? That has to be finite. So remember that L has to be finite. If it's infinite, is that useful information too? The answer is what? Yes. You know why that's useful? It's useful because it tells us end behavior. So we get to get the nice end behavior of these curves as well. All right? So this idea that we just finished is always going to be finding that limit, whether it's finite or infinite, is always going to be a part of your curve sketching. It's always very useful. So, okay, so let's check. So I need to take the limit here as x goes to infinity of, what was that curve again? I got to look back. What is that curve? It's x cubed plus 6x squared plus 9x. And what do you guys think? What's this limit going to be? I'm going to claim the limit's what? Infinity. Is that true? All right, you guys okay with that? How do I know that limit's infinity? Because as x gets big, right? What's happening to this x if I raise it to the third power again? That's getting what? Bigger. What happens over here if we raise that same x to the second power? That's getting bigger too. Not as fast as the x cubed though. And then 6 times that, which is positive, so we still do what? This is going to get what? This is plus infinity, big and big. And then what's happening to the same x? It's getting big, and that 9 is positive, so this is infinity. So if I have Oprah money, Bill Gates money, and, oh, who's that Amazon guy? Okay, I got his money too. What do you think I got? I got a lot of money. You see what I mean? That's infinity. So this is useful. What that means is, let's summarize this. This is not a what? Horizontal asymptote. However, what that means is, as x gets big, we know y gets what? Big. This is end behavior. Okay, end behavior. Anyway, if you guys recall from pre-calculus, that means your curve either looks like this, right? It's going up, it's going down. It's either concave up, concave down. Remember that? That's the end behavior. That's what they're talking about. And let's find the other limit now. Limit x goes to minus infinity of x cubed plus that 6x squared plus your 9x. Okay? So now we do the same thing. Now x goes to minus infinity. So what happens here? Well, this is the same x. So we get what? Minus infinity plus, this is the same x. What do? Infinity. 6 times infinity is what? Positive infinity. What do you do here? Is that negative infinity? Uh-oh, what's this? Anybody notice a problem here? Yeah, it's indeterminate here. So since it's indeterminate, I guess I have to use algebra. And in this case, they just mean to factor. All right, so let's factor here. So what I'll get now is this is the limit as x goes to minus infinity. Now, factor out an x. I get x squared plus what? 6x plus 9. Is that right? All right, let's see what happens here with this. X is going to negative infinity. Okay, what happens now with this one? I think I get what? Negative infinity here times positive infinity. Okay, this is going to be what? Negative infinity plus what? Plus 9 here. Uh-oh, what do you think happens now? This is still what? Indeterminate. What should we do then? So this is indeterminate here. So maybe we should, here's what I want to remark here. By properties of limits, okay, I have a limit, x goes to minus infinity here, x times the limit here, x goes to minus infinity of what? What's left? X squared plus 6x plus what? Plus 9. Is that true? And this is indeterminate right in here. So since it's indeterminate, I have to, again, use what? Use algebra here. And the only type of algebra I can do is what? I can factor. So factor this, x, and what do you have here? X plus what? 6 plus, anyone want to tell me? How do we get 9 over x? How do we know to factor it that way? If I factor out that first variable, right, factor an x out, remember this? This has to be the quotient here. Remember that? That's the quotient. So I take every one of these terms and I divide by what? By that x to get the quotient. Now, a couple of things we could look at here. This is going to be the limit now as x goes to minus infinity times x times the limit here as x goes to minus infinity x plus 6 plus 9 over x. And don't forget out here, you already had that limit as x goes to what? minus infinity for the x. Okay? You guys okay with that? I just bring down that first one. So, let's see what happens here. We know this is minus infinity times what? Minus infinity for these first two. Is that right? So we got this limit here already. We got this limit here. Those are both minus infinity because x goes to negative infinity. Now, we have to find out what's happening here. What do you guys think is happening here? If we focus on this, by properties of limits, you essentially have this, don't you? You got the limit x goes to minus infinity of x plus the limit of a constant. And I guess I want to write it this way here. Okay, so you guys can see how that algebra helped us. So this is going to be what we're looking at here. You got the limit now as x goes to what? Minus infinity of x plus the limit of 6 plus 9 times that limit. We still don't have enough space. Start over here. Limit x goes to minus infinity of x plus the limit of 6 right? Plus 9 times the limit of 1 over x as x gets to minus infinity. So, I want to put in words here. We use what? These are properties of limits. So, by properties of limits, let's see what we get. Don't we get negative infinity plus 6 plus, that's 9 times 0 because of the fact that this limit over here is going to be what? 0. So that's kind of gone. I could get rid of that. And again, now if I what? If I owe Oprah money and I have $6, what's the deal here with this? This is still going to be what? Negative infinity. So let's summarize this here. I got minus infinity times minus infinity, and this whole thing here that we just did is also what? Minus infinity. So what's negative infinity times negative infinity times negative infinity? This is negative infinity here. So our conclusion now is going to be as x goes to negative infinity, where does our y go to? Negative infinity as well. That's going to be our end behavior. Okay, this is not a, since we don't have a finite value, this is not a horizontal asymptote. All right, as you guys can see, this is going to be some work here. Okay. Yes?
Couldn't we just factor x squared plus 6x plus 9 to x plus 3 times x plus 2?
You could have done that too. Good job. In fact, there's a couple of things you guys could have done. Believe it or not, I could have started this here from the beginning and factored out x squared. Oh, you don't see that? Yeah. Let's go back here. This doesn't want to close. Okay. Where are we at here again? This x squared. Oh, yeah, you could have done that too. Good job. Yeah, at that point, this is a good observation. See this term? See this word using algebra? What could we also do? Factor that. So you could have factored this as well. And that would probably be, should we erase all this other stuff since you have it in your notes already? Let's see how that works. Okay. Is it factorable, by the way?
Yeah.
wonder if you can increase the size of the eraser on this. Here we go. All right. Let's try to factor that. This is x plus 3 times what? X plus 3. So that would be a nicer way to do this. Limit x goes to minus infinity, x times limit goes to minus infinity. We can say, if you guys want, x plus 3 to the what? Second power? So this is going to be negative infinity, and this will be negative infinity plus 3 is still going to be what? That's negative infinity squared, which is, and that's going to be minus infinity. Good. So that's a lot sweeter. Yeah. Okay, remember, x is going to negative infinity here. So you got the same conclusion, though. But yes, you could have done that, too. It's a lot nicer. Okay. All right, now what comes next with this? We did the asymptotes, is that right? And we know there's no vertical asymptote, so what comes next? I can't see in our guidelines. Oh, intervals of increasing, decreasing. So now, what comes next are your intervals of increasing, decreasing. So since our function here, right, what's the function again? X cubed, I should put this here with me, x cubed plus 6x squared plus 9x. This is where you're going to start to use your derivatives, remember? This is really sine analysis on the first derivative. So let's write that down because we never want to forget that. Sine what? Analysis on that first derivative. So at this point, you guys should know how to do these derivatives in your sleep. Is that right? Okay, I won't actually go through. Well, I won't actually go through all that. Just let you guys know. This will be what? 3x squared plus 12x plus 9. That's my derivative. I got to do what with this? Sine analysis now. So when you go through your sine analysis procedure, right, your first step is to find where that equals 0, right? Got to find your critical values. So note this. Note your critical values here. Right? Critical values where the derivative is 0 or the derivative does not exist. So here we go. 3x squared plus 12x plus 9 equals 0. Factor out your 3. X squared plus 4x plus 3 is 0. And you get x plus 3. X plus 1 equals what? 0. Okay, you guys okay with that? Did we factor that correctly? Well, before we do this, you guys notice what you could do with this 3? You know what this implies? This implies that x plus 3 times x plus 1 is 0. We know this for a couple of reasons. Because whenever you multiply 3 terms together and the answer is 0, right? I know the first term out here is a constant 3. So this is not actually 0, is it? It's not making your product 0. What's making your product 0 is these other two terms. So I could go straight to say that the other two terms, that product has to be 0. Sometimes students rather do this. They rather say, Mr. Judge, could I have just done what? Divided 3 to both sides, and then my 3's cancel here, and 0 over 3 is actually 0. The answer is yes. You could do that too. So now, x plus 3 is 0, or x plus 1 is 0. Subtract your 3, subtract your 1. So we'll get x is negative 3. X is what? Negative 1. So for sign analysis again, we found those critical values on the first derivative. So remember, -3, -1, first derivative. These are the locations where that derivative is 0. These are the critical values, right? And this partitions our axis. So our partitions our axis where? Region 1, region 2, region 3. So at this point, what do we need again? Do you guys know? Test points. Give me a number to the left of -3. -5. Okay, give me a number between -1 and -3. -2. Give me a number to the right of -1. Okay, these are all test points. So at this point, again, go back to what that derivative really is. We found this derivative to be, now I always think that the factored form is always the best form to use. So if I have this already factored, x plus 3, x plus 1, this is going to be very helpful. I'm going to now plug in what? Plug in -5 here. What do you guys know about that first derivative here? Is it positive? So I got 3 times, looks like -2 times -4. Yeah, I don't care about the answer. I care only about the sign. It's positive, right? Is it positive?
Yeah.
Double check. Okay, repeat the process now. This time, what's the test point? It's -2. So you're going to plug in here -2, -2. I don't really care about the what. Answer, just the sign. 3 times +1 times -1. My answer is what? Negative. Okay, plug in what? Plug in 0 now. Test 0. So we end up getting now here 3 times 1. I don't care about the answer. I just care about the sign. That's positive. So I'm going to have some nice information. This is where my curve is what? Increasing and what? Decreasing. So what I actually do, I actually do the following. Remember, we do what? That's a increasing slope for a positive, is that right? For a positive slope in that interval. Tangent line is positive. And then we got decreasing here. And then we got what? Increasing. So this is where I say to you guys, a picture is worth what? 1,000 words. What do I mean by that? If you're standing here, where are you at? A relative max. If you're standing here, where are you at? A relative min. So here's our conclusion. What do we write down? F is increasing on what interval? Negative infinity up to what? -3 union what? -1 up to infinity. F is decreasing. You say, where's the function decreasing? -3 up to -1. Okay, because your positive interval here is 1 and 3. The negative is 2. So this actually gives us some nice information. Now, if you notice the next portion of this, they say 5 and 6, right? Intervals of increasing, decreasing. You got local max, local min. So what does that mean here? We also have what? a local max, where's the local max going to be? A local max happens at x equals which value? Negative 3 right here. See this? Okay? You're standing on top of a what? Of a hill. So it happens at negative 3. In fact, what's the local maximum value going to be? Let's put it down here. The local max will equal f of negative 3. So I have to go back and plug everything in here to my original function, not the derivative. See the original function? Oh, way back here. I got to plug in what here? Negative 3. Okay, the x coordinate value, I plug that in. And what do you guys end up getting here, by the way, if you do that? Because we want to find that local maximum value. Y will be negative 3 cubed, right? Plus 6 times negative 3 squared, plus 9 times negative 3. I think I get a negative 27, plus 6 times positive 9. Is that minus another 27? So I get negative 54 plus positive 54. What is that? Is that 0? Okay. So that's our local maximum value here. That's equal to 0. Okay? Now we also have a local min at x equals, where's the local min at? Negative 1. But what is the local min? The local min will be f of negative 1, and I do the same thing. I just got to go plug in what now? Plug in negative 1 here. So let's see what this equals when I plug in negative 1. Okay, when I plug in that negative 1, what do we get? Let's see. We get negative 1 cubed, right, plus 6 times negative 1 squared, plus 9 times negative 1. I got a negative 1, plus 6 minus 9. What do we get? Is that negative 4? I hope so. So this value will be negative 4 now. Okay? So this is what we have to find for what criteria again? You're finding this for what criteria? Which is that one? Number what? Number, that was 5 and 6. So notice when you do sine analysis on the first derivative, that's good information. Gives you local max, local min, increasing, decreasing. What about number 7? What's that last criteria? Concavity. Right? And when you find concavity, what do you guys always remember again? Sine what? Analysis on your second derivative. Okay? So we need the first derivative. What was the first derivative of this function? What was it in your notes, that first derivative? Is that right? So our second derivative is going to be what? Take a derivative of the first derivative. And what do you get? 6x plus what? Plus 12. Okay, good. So I have to use sine analysis on this. That's kind of nice because I have to set this equal to 0, right? We get 6x plus 12 is 0. Subtract your 12 and we get what? 6x is negative 12, or x will be negative what? 2. So remember, we're doing sine analysis. And negative 2, we got the second derivative here. That value will be what? 0. Quadrant 1, quadrant 2. Test, maybe at negative 3. Test point. 0 is available. I like using that. And again, we're going to have to test now the what? second derivative. So if you like I said, if it's factored, it's a little bit easier. We can say f prime of x will be 6 times x plus 2, right? So plug in and test the value -3. And so when you do that, what's your sign? Let's keep that red, I guess. 6 times, oh, I guess it's what? It's negative, is that right? So double check, we plugged in a -3. What do you guys plug in now? Plug in 0 now, test 0. So if you're going to plug in 0 now, you get 6 times 2, which is positive. There you go. And you got concave what here? Concave down, and this is concave what? Up. So here's our conclusion. Our curve now is what? F is concave how? Down. Where are you concave down? From negative infinity up to -2. F is concave up. Where is that going to be? School wants us to log on. This is going to be from what? -2 to infinity. Is that right? You know, and if you wanted, you could say, what does concave down look like? You don't hold water. What does concave up look like? You hold water. What's interesting at this point here, -2. Anybody want to tell me? What's that again? What does that mean? You have an inflection point, right? So F has an inflection point at, what's the location? X equals -2. But a point has an address. Okay, this point on the curve, now your inflection points always have to be on the curve. So at -2, what's the y-coordinate value? You're going to have to go all the way back to the original what? Original question again. You're going to have to plug in -2, is that right? So I get -2 cubed plus 6 times -2 squared plus 9 times -2. That gives me a negative what? 8 plus 24, double check, minus 18. And what does that equal? That's like minus 28. Is that -4? -2? Let's see. -8 plus 24 will be positive what? 16. Is that right? 16 minus 18 is what? -2. Okay. So there's our inflection point at -2. All right, now what do they want us to do with this? Yes, at this point we have to sketch the what? The curve or your graph, whatever you want to call it. So let's take a look. I want to show you guys something here. By the way, this is, what was this original curve here? Y equals what? X to the third power, right? Plus 6, x to the second power. And then plus, I think, what? 9. Is that x? Okay. Now, this point here, well, I guess I can't write on this here. Here's, well, let me see. There we go. What's so special about all these points that you got? Can you see these points here, by the way? Let me go over here. See that little there? That point, that point, that point. This is your x-intercept and y-intercept, right? Yeah. This is going to be your local what? Local mean. What's this? Local max, is that right? And aren't you increasing here, and then decreasing, and then what? Increasing forever?
Yeah.
Isn't this concave how? Down, and then concave down, and you got concave what? At some point, an inflection point, you change concavity, that's concave left. So I want to show you guys this rough picture here, because we're going to need to do what with this? We got to sketch this stuff. So this is kind of formally what you would have to do. Let me try to see if I can do this here. I did have a some of these here somewhere. Anyway, I had some axes. Not that. Let's not use that one. Yeah, anyway, okay, I did have some axes here, and maybe we have to go out and find it where, let's go, oh, it doesn't even have all of them here. Yeah, I thought it was in recent. I thought it was in recent, but it's not. Okay. Oh, okay, whatever. I'm going to have to. I apologize. Okay, let's try to graph this so you guys can see what's going on here. Kind of a rough sketch. I wanted to use already what I had. I know where it could be. Let's go over here. Graphing quadratics. I'm going to use something like this here. Come on. You got to be able to pick this up. Yeah, I had some I have these graphs here somewhere. Recent notes. Let's go back here. Here we go. You guys know what we're talking about here? That would be now you should be able to make this bigger. Anyway, you know what we're talking about here? Let's, how do you get that bigger, you guys know? Anyway, we'll try it right here. Okay, go back to the increasing, decreasing. Go back to the x and y intercepts. You got at 0, -3. Is that right? So let's try this out. I'm going to put a point. Zero, 1, 2, -3. Those are our x-intercepts, right? Y-intercept. And then what do we have again? Local max and local mins. So go back. We got our intercepts. Yeah, 0 is -3. And what else do we have? We got end behavior, good. And we got our local max, local min. Oh, at -3, -1. Is that true? So you're going to have to help me here. At x is -3, we have a local what? Max. So we're standing up here. And what's the other value? X is -1. We have a local min. But what was that location? -4. So I go to the left, -1. I go down 1, 2, 3, 4. There you guys go. I'm standing how? Right there. Is that right? So local max, local min. Now remember, how does this look? We're going increasing, decreasing, and then increasing. And this is forever. See how this looks here? Increase, decrease, increase forever. So in some ways, you can sketch it that way. This is what I do. Increase, decrease, and then increase what? Forever. That's pretty much how this curve looks. Increase, decrease, increase forever, right? Now you might say to me, what about the other information? What about the concavity? Well, concavity on this interval from 0 to -2, you're concave what? Down. So I have to adjust my sketch, really. Let me do this. At -2, we got another point. What's so special at that point at x is -2? -1, -2. What's the y value? -4. Is that right? There's my inflection point. So you can sketch a very nice what? Concave down here now. There's concave down. Notice this goes down forever. We had that end behavior. And then at -2 here, see that -2, I have to sketch concave up. Is that right? So hold water, and then this goes up forever. Now, you want to draw a nicer curve than this, and if it was bigger, I'd probably be more successful. This goes up forever in terms of the end behavior, but you always start with this increasing, decreasing, finding local max and mins, going through these important points. And then notice this here. Okay, let's draw nicer. Is that somewhat, and make sure this is round over here, is that somewhat like the picture that we have over here? Okay, you guys see what we're saying? So yeah, so this is how you go about this sketching a curve. Now, this is only one. I have a few more for you guys to try out, but this is where we're at. So anyway. Okay, let's try some of these out here. Let's see what's going on. Yeah. You got to make sure that there's sound coming through here. And it looks like there is, hopefully. Okay. Well, we're going to go over these curve sketching guidelines again. So let's recall we had some of these details. There's going to be a lot of work here. So at first, I would say it's probably a really good idea to make sure you know what kind of function this is, right? So because this function is rational, it's a fraction. We have a rational function. What we know always for rational functions in terms of the domain, they're defined everywhere except where, let's undo that. They're defined everywhere except where the denominator is 0. Is that right? Okay, you guys okay with that? So we have to find where that denominator is 0, and all we do is set the denominator equal to 0, so we know for the domain, this is where we're at, 1 plus x equals 0, and solving for x here, we know x equals negative 1. Now this is the value of x where you can't equal negative 1. Oh, excuse me. Yeah. Okay. All right. So, okay, so we know that x could not be negative 1, so let's put that here. So for the answer for our domain, if you guys recall, we can say it this way. We can write it in set notation. It's a set of all real numbers x such that x could not equal negative 1. Now, remember from pre-calculus another thing too. Okay? From pre-calculus, when you have a rational function, this is also the location of your vertical asymptote. Is that true? All right. So we know, let's just remember that your vertical asymptote will happen at x equals negative 1. So we're going to have some of this detail here we're going to use. We're going to use the domain and the fact that our vertical asymptote is at negative 1. And this is the first part. Okay, we're finding that domain here, right up here. So we check that off the list. And the second part here is going to be to find our intercepts. So we're going to need x-intercepts and y-intercepts. So go through your procedures for finding both those x and y intercepts. Okay, so remember, to find an x-intercept, always you follow this set of instructions, right? You're going to let y be 0, and you're going to solve for x. So in this case here, what that means, if we go back to our original equation here, right? This is our y variable. Y is f of x. So we're going to let this be 0 here. And when we let that be 0, we get 0 equals 1 minus x over 1 plus x. I prefer the 1 minus x over 1 plus x to be equal to 0. And again, we're going to say that this is a fraction, and a fraction that's equal to 0 only happens when your numerator equals 0. Okay? The fraction is undefined when the denominator is 0, but a fraction equal to 0 only happens when that numerator is 0. So if you recall, I usually give this to students. If you have a fraction and that equals 0, then what that means is that numerator is actually 0. So that's what we're saying here. Okay, so this is something you guys can remember. And what that means now is we're going to have to set 1 minus x, that numerator, equal to 0. And we're going to have to solve for x. So I can add x to both sides. And I end up getting here 1 equals x, or simply x is 1. Okay, so this is the location again of my x-intercept. And formally as an address, that address is going to be 0, 1. So this is the location of my x-intercept. Okay? We also have to find not just the x-intercept, we need the y-intercept value. And to get the y-intercept here, we're going to let x be 0 now. We're going to solve for y. So this is our procedure for finding the y-intercept for any function. So you go back here again to your original equation, right? This time, x is 0. Okay, this is my y variable again. And so I get 1 minus 0 over 1 plus 0, and that's just 1 over 1. We know that's also 1. So the formal address here for our y-intercept is going to be, letting x be 0 again here. Solving for y gave us that 1 again. So this here is going to be, again, this is our y-intercept value. It's at 1. So we went back, and again, we let x be 0 here and here. That gives us y equal to 1 over 1, which is actually going to be 1. Okay. So after we find the intercepts, we have them. We have the vertical asymptote. We have the domain. We then go to this concept here of symmetry. Okay? And so notice this. Because this is a polynomial, strictly, a rational function, where your numerator is a polynomial, the denominator is a polynomial. We'll be looking for whether the function is even or odd. Okay, in this particular example, if it was a trig function, you were going to look for whether it's periodic, right? So it could be even, it could be odd, or it could be neither. And that might help us in our curve sketching. So we're going to look at that analysis as well, see where this function is even, where it's odd. Now, we have to go back and look at those definitions again of being even and odd. So we have to go with the function here. Let's get rid of this. We're going to write down this function. 1 minus x, 1 plus x. So, under the symmetry, our function here is 1 minus x over 1 plus x. Okay, bless you. All right, you guys okay with this one? Now, what I'm going to say now again here with this is going to be, what's your definition for an even function? Okay, so let's remember, f of negative x has to be the same as f of x. And that is really the definition of being even. So let's even recall what we said last time, that typical functions that are even are like x squared, x to the fourth, really x to any even power. And then we think of the trig functions, right, which might be even. What trig functions might be even, if you guys remember? I think the only trig function that's even is what? Cosine. And actually, believe it or not, since cosine is even, so is what? So is secant. Okay, so these are kind of some functions that we already know. Being odd again, just to remind you guys again, odd functions is when f of minus x is equal to f of x, and that's minus f of x, sorry. So we're going to pay attention to this detail here, this negative x. When those things are satisfied in your definition, we can say the function's even or odd. Now, x, x cubed, x to the fifth, these are some typical examples of odd functions. And sine is an odd function as well as tangent, as well as their reciprocals as well. Okay, so you have the reciprocal of sine, reciprocal of tangent. Reciprocal of sine is cosecant, that's going to be also odd. Reciprocal of tangent is cotangent, that's also odd. So we do have some various functions that are even and odd. Now, again, we're just going to test this function and how you really do this. And so you can actually put this here in our notes. So we're going to find or look at f of minus x. And that just means wherever there's an x here in your function, okay, there's an x here, there's an x here, there's an x there. We replace that x with a minus x. Okay, so double check to make sure we just did that. Now when we simplify, we see that f of minus x becomes 1 plus x over 1 minus x. And to point out to you that this does not equal my function. Okay, because my function is way back over here. Okay, it does not equal, it's not the same. Is it opposite in terms of sign though? Right? Let's check that. Is this function the same as minus f of x? And if we take that negative sign and our function is f is 1 minus x over 1 plus x, remember this sign here gets distributed to either the top or the bottom, but not both. So if we distribute this to the top, what we're going to see here is that this function is negative 1 plus x over 1 plus x, which is the same as x minus 1 over 1 plus x. Now, this is minus f of x. So as we can see now here, f of minus x, is that the same as minus f of x? Well, what's f of minus x? That's right up here. Let's go back. Here's my f of minus x, which is 1 plus x over 1 minus x. Okay? So if you want to put the negative sign in the bottom now, maybe you say you want to do that. So I want to say here that this so far looks like it's what? That it's not equal to minus f of x. If we put the negative sign at the bottom, that makes this positive, and then that makes this sign going to be what? Negative. And so this is f of minus x, and it's not the same as minus f of x here. Okay? Oh, let's double check here. Let's hold on here. F of minus x is what you see right here. Is that right? Is that right? 1 plus x over 1 minus x. So minus f of x is right here, minus sign. Put the minus sign where? At the bottom. So we'll get, here, let's try this out. Let's erase this here. Let's try this again here. Let's see what minus f of x is going to be. It's a negative sign, and f of x originally is 1 minus x over 1 plus x. And that's going to be, if we distribute our negative sign at the bottom, we get negative 1 minus x. And yes, that's not the same. So we were correct here. Okay. So that's not the same as f of minus x, so you know. Okay. So what that means is the function is neither even nor odd. So in terms of symmetry, we're going to say that this is under that neither situation if we go way back up here. Okay? So here's the neither. So symmetry has no symmetry. So let's continue. After symmetry, what do we know we have to do? We have to find the what? The asymptotes. Now we already know you have a vertical asymptote, so that's done. We have to find the horizontal asymptotes, right? So under asymptotes again, vertical asymptote happens where x equals, is that negative 1? So we have to find the horizontal asymptote now. Now that's going to be looking at the limit as x goes to infinity of the function. And our function again is, what's the function? Y minus x over y plus x. So if we ask you guys here now, how do you find these limits? This is limits at infinity. So this is one limit we have to look for. The other limit we'll look for is minus infinity. So in some sense, we're looking at end behavior for these vertical asymptotes. Or sorry, horizontal asymptotes. This is where we're at. This is AKA the end behavior. So, if you guys remember, what do? How do you take limits at infinity here, right? Do you guys remember? You always divide by what? The variable with the highest power in the denominator. And you divide every term with that. So, this limit, x goes to infinity, 1 minus x over, let's leave ourselves some space here, right? 1 minus x over that x, 1 plus x over that x. That's again the limit. X goes to infinity. 1 over x minus x over x. 1 over x plus x over x. So your first limit's going to give us, as x goes to infinity, 1 over x minus 1 over 1 over x plus 1. Okay, you guys okay with that? Isn't that what we did before? We've done all this. And so now as x gets big, right, what do we notice with this portion here by properties of limits? This goes to 0. This goes to 0, right? Properties of limits say this will be 0 minus 1 over 0 plus 1, or we can say negative 1 over 1, and this limit is negative 1. So as x gets big, y goes to negative 1. Okay, so this is going to be the location of a horizontal asymptote. So let's write that down. Now this is our first limit. This is as x goes to infinity. We have to see what happens as x goes to minus infinity. So we're going to go in the other direction now. So for that limit now, x goes to minus infinity. You have 1 minus x, again, over 1 plus x. It's the same process where you divide every term by the variable with the highest power in the denominator. You're going to divide by x. So that limit will be x goes to minus infinity, 1 over x minus x over x over 1 over x plus x over x. So we get the limit as x goes to minus infinity, 1 over x minus 1 over 1 over x plus 1. And so as you guys can see, take your limits and use properties of limits. This portion is going to go to 0 again. This goes to 0. And you obtain now negative 1 over 1, which is going to be negative 1 again. So what this means is, as x goes to negative infinity now, go to the left, y is going to negative 1. Okay, this again is your horizontal what? Asymptote. There's your curve. Right, sorry, there's your limit here. So we found the asymptotes. So after you find asymptotes, right, go back to your curve sketching guidelines. What do you do now after you do this? Yeah, we need to find increase and decrease. And that involves what? Sine analysis on, again, what? The first derivative. So we're going to have to take some derivatives here. So if your function is 1 minus x over 1 plus x again, we need that derivative. Is that right? So the derivative here is going to be found. It looks like we're going to need a lot more space because of the fact this is a, what kind of function is this? This is rational. Is that right? So if we have a rational function, what rule is this called again? What do we use again? Quotient rule. Good. Okay, we're going to use, again, quotient rule. And, okay, let's make sure quotient rule is applied properly. So, a couple of ways we can look at quotient rule. Again, if my F letter is taken in describing the function, so we're going to look at a rational function this way, right? And I'm going to remind you guys, square the denominator, bring your denominator up here, multiply times the numerator, or the derivative of that numerator, right? Subtract times the derivative of the denominator times the numerator here. So you might want to double check to make sure our quotient rule is really written down properly, okay? Because, let's double check. Yep, looks like we're okay. Because now we just take the what? Take the derivative here. The derivative of 1 minus x is negative 1. The derivative of 1 plus x is actually positive 1. Is that right? Okay. So, let's get the screen back. Okay, so let's find these derivatives. This will be 1 plus x times negative 1 minus 1 minus x, everything over 1 plus x squared. So if we distribute here, we get negative 1 minus x minus 1 plus x. This is over 1 plus x squared. So let's simplify here. And it looks like negative x and positive x are going to cancel. So it looks like I'm going to get negative 2, right? As a numerator, double check my work. Negative 2 over your 1 plus x squared. Now, what you could do with that negative sign is you could put it at the same level as your division sign. So this derivative is negative 2 over 1 plus x squared. Okay, so there's your first derivative. Now again, we have to use sign analysis here. So we're going to write that down. Use sign analysis on that first derivative. So sign analysis on that first derivative, if you guys remember, you have a rational function. Okay, so this is rational. You have a numerator, you have a denominator, you have that sign there. So whenever you do sign analysis, you have to find where the numerator is 0. So what I'm going to say to you guys here is, this numerator, this term on top, is not ever equal to 0. Is that right? Because you have a fraction here. And they want to know, where is that fraction equal to 0? Well, you can say negative 2 is 0, but that's not true. This never happens. So your numerator is never 0. That just means we have to be concerned now where the denominator is 0. So we're going to check here. We already checked where the numerator is 0. We noticed that it does not happen. Right? We checked this. That doesn't happen. So once we know that doesn't happen, we're going to move on to the denominator, and we want to find when is that denominator equal to 0. Okay? Because we have to find where that derivative is either 0 or undefined, right? So we have 1 plus x to the second power, that equals 0. We set the denominator equal to 0, and we're going to try to solve for x, right? So now we have to find where this is undefined, and that happens where the denominator is 0 now. So we'll put that there. So we have to solve this equation. Now there's different ways of thinking about this, right? Anytime I square a term and it equals 0, what that means is what's in that parentheses must be 0. So that means 1 plus x is 0. So if I subtract 1 from both sides now, I'll find here that x is actually -1. Now, that's going to be meaningful for us because what does this actually mean again? This derivative, first of all, let's think of this phrase here. It's never 0, so the derivative never equals 0. The derivative is undefined at x is what? -1. Okay, so in other words, what this means is our function f has a critical value, maybe, at x is -1. Now, is that true? Is it a critical value? Yes or no? I'm going to cross out this word here. Why do I get to cross it out? Because I know we're doing sign analysis, right? Go back here. I know we're doing sign analysis on that first derivative, and in the process of sign analysis, you might just say to me, okay, Mr. Judge, all I do now is in my sign analysis technique, at -1, I know that first derivative is undefined, okay? And I know that what that means now is I have only 2 regions to check. Region 1, region 2. And you might say to me, and I know, I just need a test point here to the left, maybe like a -2. And I need a test point to the right, maybe like a 0 here. But don't forget what's the domain of your function. So you always want to go back and think about that domain, right? What do we know about this function? What's so special at -1? Well, -1's not in the domain. Is that true? Okay, so it's not in the domain. What else? Since it's not in the domain, you know you have a what there? A vertical asymptote. Is that right? So if you recall, there are conditions where your function has a derivative that does not exist. One of the functions or one of the conditions is that the derivative won't exist at vertical asymptotes. Is that right? So that's all you've actually found. Okay, I just want to let you guys know. Does that mean that it's a critical value then? The answer is no, because it's not on the what? It's not on the curve. It's not in the domain. Okay, so I just want to let you guys know. But what we did find, which is just as important, is that f is not differentiable at x equals -1 because you have a vertical asymptote. Okay, so it's discontinuous at that point. All right, you guys okay with that? Just want to remind you guys. So now go back to the derivative here. If we remember what the derivative function here is, our derivative is -2 over 1 plus x what? Squared. Is that right? So what do you guys know about this here? If I test the value -2 now, right? I'm going to plug in -2 for x. What does that give you? Anybody know? Yeah, I get -2 over, it looks like I'm going to get what? -1 squared. Now, I really don't care about the answer. I don't care about the value. I only care about the sign. So even though I know -1 squared is +1, I just know it's positive. What I have here is a negative divided by a positive, and what does that give me? That gives me a what? Negative answer. So that means my region 1 here again is negative. Similarly, now, after we checked the test point of -2, let's test now 0 here. So I'm going to plug in here a 0 for x. And notice what do I get now if I plug in a 0 here? Anybody know? You get the same thing? Yeah, I think you get the same thing, right? What do you get? You get what? -2 over 0 plus 1 is 1 squared. I don't care about the answer. I just care about the sign. And the negative over a positive is, again, going to be a what? It's going to be a negative. Okay, you guys okay with that? So region 2 is also negative. So remember at this point, what we do with this here is what I do here is I notate my curve is decreasing, my curve is what? Decreasing. So what would you guys say happens with this now then? Right? We can say something here about this. Our function now here is what? How do we conclude all this here? Let's go back in and say something here. Let's make a note here. My function f is decreasing. Under what interval? Negative infinity up to -1, union -1 up to positive infinity. So I want you guys to be very careful here. That at -1, your derivative is undefined. Being undefined is exactly that. You're not defined. So the derivative is only negative in the quadrant 1 and quadrant 2 here, or I should say region 1 and region 2. Okay? So in those two regions, you have a function that is what? Decreasing. And furthermore, is this function increasing ever? The answer is what? No. So I want you to also know that f is not what? Is only decreasing. Okay, there's no locations where your function here has a positive derivative. There's no regions here. Okay, it's strictly negative, so it's decreasing, decreasing. Let me also say something about your curve here so you guys know. What comes next after your increasing, decreasing in your curve sketching guidelines again? Yeah. We have to go back and talk about the what? Local max, local min values. So for local max, local min, what do you think is going to happen here? Anybody have an idea? Does it satisfy our definition of having a local max or a local min? The answer is no. So we also know, looking at this picture here, we also know that f has what? No local max. It's kind of weird. No local max or a local what? Min. Okay, so that's important information too. Go back to this. And if you remember, why doesn't it have a local max or min? Because it doesn't have a valley and it doesn't have a hill. Is that right? So no local max, no local min. Let's make sure we put that down because there's no valleys and there's no hills. All right. Now, what is that? What comes next after this? You guys know what comes next? Concavity, is that right? Concavity and inflection points. So for concavity and inflection points, sine analysis again, but this time it's on what derivative? On your second derivative here. So we're going to go through all those guidelines again on the second derivative. We're going to go over this again. So in order to find the second derivative now under concavity, remember you need the first derivative, right? So your first derivative here is, I'll put the -2 on top, 1 plus x in parentheses squared. So this time for the second derivative now, again, we're going to have to use what again? What rule do we use? Quotient rule. Right? Can I use quotient rule? What about this? Let's note. What if I write my function as -2, 1 plus x to the -2? Can I do that? Say what? Yes. Okay, and so you might say, why would I do that? Well, it might make things a little bit what? Easier to take the derivative. Now, if you take the derivative, it's really going to be now what? Power rule, is that right? Combined with what? Chain rule. So I think I'm going to choose that this morning. So my second derivative will be just differentiate the first. So remember this. -2 times -2. Is that right? I think I wanted to do that, but -2 times -2, or what I could do is this. Let's bring out that -2 in case you guys wanted to do that detail. Could take out your constant, right? Anyway, it's going to be the same thing. So -2 gets multiplied to that -2, I guess. So I'll get -2 times -2, 1 plus x, -2 minus 1. Is that true? Now this is the power rule portion. I also have to use the what? Chain rule. So far over here, power rule, and now what? Chain rule. So here's what we get. -4, 1 plus x to the -3 power, and the derivative of 1 plus x is actually just going to be 1. So this is times 1, or we can simply say the second derivative is -4 over 1 plus x to the third power. +4, thank you. I'm not awake. Thank you so much. Gonna have to drink more coffee here. All right, good job. Now, what we do here is what? Sine analysis on the second derivative. Again, since it's rational, right? Set your numerator equal to 0. And you might say, I set 4 equal to 0. Yes. Well, 4 is never what? 0. So what that means is my second derivative function is never 0. Okay, that's useful. And then now, for sine analysis, we set the what? Denominator equal to what? 0. So 1 plus x to the third power equals 0 really means that 1 plus x is 0, because if you're going to cube anything and it ever equals 0, what that means is that base has to be 0 to begin with. That's the only way that happens. I could subtract 1, and now I get x is -1 here. So I know my second derivative is undefined or does not exist, right? At what value? X is -1. So in terms of sine analysis, that's very useful. Let's see if we could do this. Because we can say at -1, the second derivative is undefined there, or it does not exist, right? However, I want to point out to people here, is -1 even in the domain? Nope, because you have a vertical asymptote there. Remember that? So I want you guys to always consider that, you know, at -1, you have that vertical asymptote. Okay, now use test points again. We could use -2 again if you want. We could use 0. I always use 0 if it's available. I have, again, 2 regions to test in terms of my sine. And now we have to test what function, though? You test now the second derivative. And the second derivative is actually 4 over 1 plus x to the third power here. Okay? Now, I'm going to say something to you guys that's going to be interesting in that you can plug in the values. Okay, you can say, okay, I'm going to test -2, so I'm going to plug in -2 here, right? What I'm going to point out to you guys is that the fact that you're cubing this, it doesn't matter, well, I guess I'm sorry. What's 1 minus 2? Is that -1?
Yeah.
Okay. 4 over -1 cube, what's that going to give you? Is that negative? So I have a positive over a negative. What does that mean about that region? It's negative. We're going to test now the other value. We're going to test 0 now. So you're going to plug in 0 now here. And I get 1 plus 0. And what does that give you again? Is that -1 or +1? It's +1. Is that right? So I get a positive over 1 cubed, which is positive. What do I know about region 2? Region 2 is positive. So this is sign analysis on our what? Second derivative. And then you might say, well, what does this tell us? It tells us where our curve is concave what? Up and concave down. If it's negative, it's concave down. Is that right? And how does that look? Like this. Doesn't hold water. What does concave up look like? Like this. It holds what? Holds water. Let's join holding water a little better. Okay. So our conclusion in terms of our analysis is this. We can say, let's get rid of the scratch work. Right? What can we say? We can say our function f is concave up for what interval? -infinity up to -1. And f is concave down for what interval? -1 up to +infinity. So we're defining here, we're actually looking at this region right here. Region 1 for concave down and region 2 for concave up. At -1, let's ask you guys this question here. This is the big question. Here's what I want you guys to know as well. Do we have an inflection point? This is important. Is there an inflection point? And maybe it's so important, I'm going to put that in red so it stands out. So what do you guys think? Do you have an inflection point here? The answer is what? Yes or no? Does anybody know why there is no inflection point? Right? Because at -1, your curve is what? It's undefined. I mean, don't look at, -1, don't look at this necessarily. Remember, an inflection point has to be a point on the curve. What have I been saying about this curve all along? What do you have? At -1, let's go back here. What have we been saying? At -1, you have a vertical asymptote. So at -1, that point isn't even on the curve. So don't necessarily come back and look at this issue right here at all. Go back and consider, do you even have, right? Do you even have a point that's on the curve at the location where you change concavity? And in this case, the point isn't even on the curve. So it can't be an inflection point, a very special point on the curve called an inflection point where you change concavity. Yes, concavity changes at that location, but that location isn't a point on the curve. In fact, you know that that location is a vertical asymptote. So you cannot say that this has an inflection point. So this is going to be a no inflection point. And again, because it's not even a point on the curve. So we're going to say there's no what? inflection point. Okay? It's not even on the curve. All right, so we did all the analysis. This is a pretty good kind of question to do analysis for. So we got concavity and inflection point. We did everything that we're supposed to do here. And so we're going to say now what you can do here with this is this. Now at this point, what do? We what? With all this information, we're going to do some what? Sketch the what? Sketch the curve. So, let's try to sketch this curve. And let's see if I can find what I'm looking for. I think I go to what? No, not here. Photo library. Boy, look at this. Where is my graph paper? There it is, April 8th, 2016. I don't even know what year we're in now. So as you guys can see, I've been doing this for quite some time. And let's undo. Okay. You go all the way to 2016 again, okay. All right, so let's try to sketch these curves. Now, I know my domain says to do what? It's everything but -1, I believe. Is that right? So at -1, what do you guys know you have again? Is it -1 or +1? -1. You have a vertical asymptote. Is that right? So I'm going to sketch this here for you guys. This is where x equals -1. I think we have a horizontal asymptote where as well. Where is this? Do you guys know? Is it +1 or -1? Got to go all the way back. Where is our vertical? Oh, at -1 as well. So y is -1, which is a horizontal line. So also at -1, you have a what? Yeah, you have these vertical asymptotes. Okay, you guys okay with that? Now, what's the location here of our intercepts? Where do you have an x and y intercept? Let's go back. We got to find our intercepts here. Well, we got an x-intercept where? Oh, 0, 1. And our y-intercept, something's bothering me here. Yeah. Here we go. It's back here. I'm glad we went to double check. Good. Yes, we got to really wake up. Okay, x is 0. Wait a minute. X is 0, y is 1. I think it's the first one. Yeah, there we go. Okay. X-intercept. 1, 0. Good. Okay. X-intercept, y-intercept. Be very careful there. Good, I'm glad we fixed it. So 1, 0, and what's the other one? 0, 1. So I'm going to do this here. X is 1, y is 0. That's right here. And then 0, 1 is right here. Is that true? So I have these locations here, if you guys can see that. Those are my what? My intercepts. Is that right? I'm talking here. 1, 0, and 0, 1. X and y intercepts. Okay, now what do I know? What do we use now? your curve, ladies and gentlemen, essentially looks like this. See that there, this portion I'm looking at? This is where this curve really looks like. You are decreasing to the left of the vertical asymptote forever. And you are decreasing to the right of that vertical asymptote forever. Okay, you guys okay with that? So you're decreasing here and here. So it's strictly decreasing. And so how do we actually write that down here? Well, if you're decreasing, this is going to be, if you look at -1 here, see this here? This is region 1 and this is region 2. Okay, you guys okay with that? So the question's going to be, since I'm decreasing forever, in region 1 on the left, right? This is region 1. If you guys can see that here. Everything to the left of -1 here is region 1. So this is what I'm talking about. Region 1, region 2. I'm decreasing in region 1. How would that look? Am I going to be in this quadrant up here, the third quadrant, or am I going to be down here? In other words, quadrant 1, quadrant 2, quadrant 3, quadrant 4, and I realize that this is kind of bad, notation, because we're using the same kind of notation for both. Nevertheless, how is that going to look? How do you guys think that looks? If I'm decreasing, am I going to be in the bottom in quadrant 3? Or am I going to be in quadrant 2? How do I decrease forever? Remember, to the left of -1 here, right, to the left of this, what am I doing? I'm decreasing. And to the right of this, I'm decreasing. So how could that look? Do we know? It's going to be on 1 or 2? How do you think we find out? How about if we try this? Go back to the function. What's your function here? Y equals, what was that? 1 minus x over 1 plus x? So if I say to you guys, let's check. Give me a value of x to the left, -1. We've been using like -2. Is that right? So if I plug in this value here, -2, what do I get for y? That means y will be 1 minus a minus. And x is, this is 1 minus 2. 1 plus 2 over -1. What do we know about y? Is that -3? Is that true? So when x is -2 now, y is what? 1, 2. Y is right here, -3. That's the location here. So I have information. What that means is my curve here is not really defined up here. It can't be. Is that right? Because you can't pass these boundaries in red. So you have a decreasing situation that looks like this, because the point is in quadrant 3 now. And you know that your curve is in quadrant 1 because you have points up here in quadrant 1. But it's also decreasing in quadrant 1 here. Okay? So this is what this means here when you're talking about what? This decreasing here. Okay? This is what we're looking at here. Points to the left and then points to the right. And then we know about concavity again, and to the left of -1 here, you're concave down. To the right, you're concave up. So you might say, what does that mean? Well, we have to hold water and not hold water. Is that right? So not holding water, how does that look to not hold water? That looks something like this, right? And how does that look to not hold water here? Well, it looks like something like that, or hold water. So to remind you guys, this is going to be here where you are to the left of -1, you are concave down, and to the right, you are concave what? Up. So you're going to kind of sketch the curve this way where it holds water, or it what? Does not hold water. Now, this is just a rough idea of the sketch. I just want to let you guys know we're putting these ideas together because you do have to go through, in terms of your sketch, you got to go through this point here. And so I'm going to say it looks something like this. Okay? And I go through these points. So it's going to go here, forever. And it's going to go up forever here. You get close to these boundaries here. So I'm going to remind you guys that when we sketch this, you have to go through those particular points. Forever, 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 forever. Now this is using all of the information that you guys have done the analysis for, so you guys know. Now, let's double check here. What was that curve again? Y equals 1 minus x. Is that right? Sorry. Let's go back here. Divided by, oops. Here's what we're going to do. Y equals, put a parentheses, 1 minus the x. Okay. And then we're going to divide here. Divide by what? 1 plus what? X. There's x. Okay, double check this curve here. Isn't that essentially what we've been looking at and doing by sketching? Okay, you guys okay with that? You guys see here, this special location is my what? Y-intercept. This is my x-intercept. I got my vertical asymptotes. I can show you guys there. So this is essentially what we just drew. We did the analysis for this. All right, you guys okay with that one? Anyway, there it is. So let's look at another curve here. So we can pick out some nice curves here. How about let's pick out a nice square root curve. 2 square root of x minus x. Let's try something like this. Okay, we're going to have to go through all the analysis again for this. This time, I'm going to go through it a bit faster. All right? Domain. Set of all real numbers that x is greater than or equal to 0. Is that true? You say why? Under my denominator here, under the square root, sorry. Under that square root, your terms have to be greater than or equal to 0. You can't have negative values. So my domain here, technically, yeah, it's a set of all real numbers such that those real numbers are greater than or equal to 0. Okay, so that's the first thing. So, okay, what else here? What comes next after the domain? Do you guys know? Talking about intercepts. First one is x-intercept. And by that procedure, let y be 0, solve for x. Is that right? So I have 0 equals 2 square root of x minus x, or 2 square root of x minus x equals that 0. I got to solve this equation here. Now, there's a couple of ways to do this. If this was intermediate algebra, right? Give this to your intermediate algebra younger brothers and sisters. And at that point, they would say things like this to you. They would say, now, if you translate the x, you just do what? Square both sides. And you get 4x on the left is x squared. You get a nice quadratic. We get x squared equals 4x. We can subtract that 4x from both sides, right? X squared minus 4x is 0. Factor your x out. X minus 4 is 0, right here. And by the zero product rule, what does that mean? We got two things. We get x is 0, x minus 4 is 0, so you can add 4. We'll get x is 4 here. So this is the location of my x-intercepts. So we know the address is going to be 0, 0, and 4, 0. Let's be clear this time, okay? That's the x value. So your address for x-intercepts typically look like this. Some x value, comma, 0. So these we're going to use. X-intercepts. So since I have some space here, let's look at this here in terms of y-intercepts if we want. For y-intercepts, we're going to let now what? Yep, let x be 0 now. 0, 0. Y is 2 squared root of 0 minus 0. Y is 2 times 0 minus 0, or simply y is 0 minus 0. Y is 0. So your address will always look like this. Since you let x be 0, it'll be 0 comma y generally. But since y is 0, this is the location of your y-intercept. So it's at the origin. Okay, what comes next? Do you guys know? After intercepts, I think we look at symmetry. What's our function? 2 square root of x minus x. I got news for you guys. This is going to be a neither. Let's see if you guys gonna agree. Why is that neither? Could you even replace, yeah, minus x there? You guys see what I'm saying? You got an issue there. So anyway, all right, that's good. Now, what do we go after that? After symmetry, we got neither. What do we have here? Anybody know? Oh, the asymptotes. Is that true? All right. So, what do we know about the asymptotes? There's no vertical asymptotes. Is that true? So go back to pre-calculus. You don't have a rational function. All right, it's not a trig function. There's no vertical asymptotes. What about your end behavior? What about horizontal asymptotes? Let's do it this way. And what's this end behavior here going to be here? Well, first we're going to start with the first one, right? We need the limit as x gets big for the curve 2 square root of x minus x. Okay, and that's going to go to the right. X is getting big, and then what about this one here? Minus infinity, 2 square root of x minus x. Are we going to look for this limit? Say what? No. Why don't we look for this limit here? See this here? X goes to negative infinity. What does that mean about x? X is negative. What do you know about your function? Your function is not defined for what? Negative values. Is that true? So because it's not defined for negative values, what do you think that means? We don't have to go through that limit. Your function is not even defined for negative x values. Isn't the domain x is greater than or equal to 0? So as x gets big here, positive infinity, that means x is positive, okay? So it is defined, so you're going to have end behavior as x gets big. So what is that limit going to be? Okay, do you guys know what that limit's going to be? If you go through properties of limits, you're going to say I have a limit of a difference is difference of limits. You might conclude what? This is infinity minus what? Infinity. Is that true? Because remember, x is getting big, so that gets big. And then this other x is what? getting big. Is that true? And what do you call infinity minus infinity? This is indeterminate. So in your homework, what did you guys do with this kind of question? Do you guys remember? If it's indeterminate, what's the key always? Use algebra. So let's use some algebra here. If you guys remember, the algebra they're talking about here, we can factor. And we're going to factor out, ladies and gentlemen, really the greatest common factors. So this is going to be something that people are going to have to get used to. When I factor out the greatest common factor using algebra, I need the GCF for the numbers 2 and 1. The GCF is actually going to be 1, the greatest common factor, right? You're used to that already. What you may not be used to is what happens with this. X to the minus 1/2 and x to the first power. Because you're going to factor out the greatest common factor. Now, if you remember from beginning algebra, it's always x to the what power? Smallest or largest? So, you have to determine, you're going to factor out x. This is going to be for our greatest common factor. You have to factor out the smallest power. So you have to know what's smaller, 1/2 or 1? 1/2, good. And don't forget, the rest is going to be to multiply by some quotient. This is factoring out x to the smallest power, factoring out your greatest common factor. But it's done with rational exponents now. Okay, factoring the greatest common factor with rational exponents. So how do you get this quotient? Do you guys remember? This is what people have to get and have to practice that. You take the original question, 2x to the 1/2 minus x to the first power here. And you always divide by the GCF. Okay, this is that GCF. Now by properties, or distributing your division here, we get cancellation. And this is now 2 minus, and then I use the property of what? Dividing exponentials with different powers. We just subtract the powers. Is that right? Guys, remember that? That's from beginning intermediate algebra. If you want, I have a video on that, from intermediate algebra. What's 1 minus 1/2? It's 2 minus x to the what? Is that positive 1/2? This is my quotient. That's the q they're talking about. 2 minus x to the 1/2. So I'm going to replace this q here with 2 minus what? X to the 1/2. So when I take the limit now, I look at the limit as x gets big, x to the 1/2, 2 minus x to the 1/2. Is that right? Is that what we got? Looks like. Which really is the limit as x gets big, the square root of x, 2 minus that square root of x. I make the claim that this is now doable. And you might say, why is that doable? Well, doable. X is positive. X is getting big, right? So by properties of limits, limit of a product is product of limits. So as x gets big, the square root of x also gets what? Big. Is that right? Times. Well, what's going on with this x? X is getting what again? Big. Is that true? So as x gets big, what's 2 minus that big? Negative. Is that right? That's like negative infinity. Okay, and again, it's actually getting small, so you guys really know that going to the left forever, being negative forever, is getting smaller, smaller, and smaller. It's like, it's a version of small. So that's actually, as x gets big, the 2 minus the square root of x is getting small. If that makes some sense, but it's 2 minus that. $2 minus Oprah money, still going to be Oprah money, right? It's negative. Anyway, we can now deduce that infinity, right, times infinity by the product rule is what? Negative infinity. That's determinant. So here's our conclusion. As x goes to infinity, y goes to what? Minus infinity. This is going to be, so you guys recall, this is not a vertical asymptote again. I'm sorry, horizontal asymptote. Why is it not a horizontal asymptote? Because this is not finite. Okay, you guys okay with that? It's not a horizontal asymptote. It's not finite, bless you. In order to be a horizontal asymptote, that number has to be finite, but this information is just as valuable because that tells us that describes the end behavior. End behavior for your curve. All right, there you guys go. So after we get the asymptotes, what comes next? I think what? Increasing, decreasing? Is that true? And our curve here, what's the function? F of x is 2 square root of x minus x. Is that right? Okay. So where your curve is increasing, decreasing again, what do? Do you guys remember? Sine analysis on the what? On the first derivative. So, f prime x d dx 2 square root of x minus x, and I'm going to write this as x to the what? 1/2. So by properties of derivative of a difference is difference of derivatives. Derivative of a constant times a function is a constant times the derivative of the function. Remember I said know this derivative? It shows up a lot. Right? What's this? Isn't that 1 over 2 square root of x? This derivative is what? 1. So what we'll get here is going to be 2 times 1 over 2 square root of x minus 1. Your 2's cancel. Get 1 over the square root of x minus 1. We have here a rational difference. And you might say, what do you mean? Well, I could divide by 1, right? So do you guys remember, how do you actually subtract these rationals? Do you guys remember? You have to have the same denominator. These rationals have to be like. These fractions have to be like. They're unlike because the denominators are different. So somebody asked, what did I do this weekend? I did some videos for just this stuff, meaning adding and subtracting rationals, you know. And so I'm fresh with that. I don't know about you guys. Square root of x, is that true? Isn't that 1? One over the square root of x minus the square root of x over the square root of x. They're now like. So because they're like, the same denominator, right? You keep the denominator and you add or subtract your numerators. Now, this is my first what? That's my first derivative. All right, what do we do with this again? Sine what? Analysis. So, for sine analysis, yet again, remember what this means. What do we have to do with this again, if you guys recall? You got to find, first, for sine analysis, where your numerator equals 0. Is that true? So, my first derivative will be 0 where that numerator is 0. 1 minus the square root of x equals 0, or the square root of x is 1, because I can do what? I can translate that term. Now, by the square root formula, or squaring both sides, right? Probably use the square root formula. What does this mean? X is 1 squared, or x is 1. Is that true? So this is the location where your first derivative is actually equal to 0. And I want to note the domain, by the way. What's your domain again? Set of all x such that x is greater than or equal to 0, so that's in our domain. All right, the second part. Where is that derivative undefined, right? It's a rational function. Where does that derivative not exist? Remember that? So this time we're going to have to do what? Set the denominator equal to 0. So the denominator, square root of x equals 0. What that means is x is 0 squared, or x is what? 0. So we now set the denominator equal to 0. This derivative is actually, or this fraction here, is undefined, right? At x is 0, your fraction's undefined. So in terms of sign analysis, that procedure, we're going to use this information at 0 and at 1 for that first derivative function. When x is 1, we have the derivative 0. When x is 0, it does not exist. Is that true? The derivative does not exist at 0. So when we create our regions for sign analysis now, we have to notate this. We have region 1, we got region 2, and we got region 3 again. Now, if you're really, really awake, which is I recommend you be, to save yourself some time, are you even going to care about region 1? Say no. I'm going to cross out region 1. Don't even care about that part. Do you guys know why you don't care? Yes, good. The domain of the function right here, x has to be greater than or equal to 0. That means you're talking about these real numbers here only. All right, you guys okay with that? All right, so that's going to be an important thing. That shows up a lot, in these kind of questions. So we just have to test region 2 and region 3. So a test point may be 1/2 here, right, in region 2. And in region 3, I could use 2 as a test point for the first derivative. This derivative right up here. So we're getting all the information. Now, all I do is plug in, which one? Plug in 1/2, 0.5. Is that right? So go back now and plug in 0.5. I'm going to change the color. 1/2, 0.5, 0.5. Do you guys notice something about this? 1 minus the square root of 1/2, is that going to be positive or is that going to be negative? What do you guys think? Is that positive? Yes. And is the denominator positive? Yes. You guys know what I'm talking about? So region 2 is what? Positive. With the test point of 2 now, go back to the original derivative there. Change that x to 2 now. And 1 minus the square root of 2, isn't the square root of 2 about 1.4? So my numerator is negative. The denominator is positive. So negative over a positive makes region 3 what? Negative. Okay? So I just test these values right here. Okay? I test the 1/2. I test the 2. I just check the sign of that first derivative. So this information's nice because now a positive first derivative means region 2 is increasing. A negative first derivative means the region 3 is decreasing. Moreover, you're talking, you have a what? You have a hill. So this picture is worth 1,000 words. Okay, you guys understand what I'm talking about? So you're increasing in region 2, decreasing in region 3. This information is going to be helpful. Let's actually summarize what we're looking at. What this means now is F is increasing on what region? From 0 to what? To 1. You guys okay with that? Right here. 0 to 1. Why don't we include the endpoints? Because at 0, the first derivative is undefined, so don't include it. At 1, the first derivative is 0. It's not positive, so don't include it. So these are open endpoints there. Okay? We don't include the values. That's where your function's increasing. F is decreasing. Where is that function decreasing on? From 2 to what? Infinity. Sorry, 1 to infinity. You say, well, why is that? Well, go back. Right? Your derivative is negative, not at 1, but to the right of 1, and forever. So here's our analysis of increasing, decreasing. Also, what do we know? This is nice information. F has a local max or local min? Has a local max. Why does it have a local max? Yeah, it has at x equals what value? At x is 1, you have a local max because you're standing on a what? On a hill right here. Is that right? At x is 1, you're standing right up here on a hill. And that's really kind of how the curve essentially looks, so you guys know. You're looking at a basic outline of the curve by looking at the increasing, decreasing situation. So you have a local max at 1. In fact, we also need to know the value of the local max, right? So the local maximum value will be the value of the function at what number? At 1. It's f of 1. So I have to go back not to the first derivative. I have to go back to the what? Original function they gave me, which is 2 square root of x minus what? X. Okay. So 2 square root of x minus x. Evaluate this at x is 1. So we get 2 square root of 1 minus 1, or 2 times 1 minus 1, 2 minus 1, and that's 1. So here's your local maximum value. Okay, let's summarize it right here. Local max is 1. That information, this information is going to be useful. All right, so we're going to notate that. We highlight that, but that's a lot of good information. Now we got to know about concavity. Is that right? Concavity. This is where what? Sine analysis on the what? Second derivative function. So I'm going to have to know the first derivative. So my first derivative was, anybody remember what that was? Yeah, 1 minus the square root of x over the square root of x. I need the second derivative. So what rule do I use? Quotient rule. So I take the denominator and I square it, bring the denominator up here, differentiate my numerator. subtract the numerator. Differentiate the denominator. Boy, all the way to the end. I hate that. Square root of x. Now, as you guys know, it's like I said, this shows up a lot, right? It's going to be negative now. But anyway, 1 over 2 square root of x. This also is what? 1 over 2 square root of x. Okay, let's put this all together. This is times 1 over 2 square root of x minus 1 minus the square root of x times 1 over 2 square root of x. Don't forget, this is all over what? X. Let's look at the arithmetic. Square root of x squared is just going to be x down here. Is that right? All I did was plug in this derivative here, plug in this derivative right over here. So if you guys took a look at that, now by some algebra here, was it negative? I hope so. Let's double check. Where's our first derivative? There we go. See this here?
The first, on the second derivative, the first derivative of the 1 minus the derivative of 1 minus the derivative.
Quotient rule. Let me double check everything. Yeah, I think we're good. This here is always for the quotient rule what?
Derivative of the 1 minus root 8.
Ah, good man. Thank you. Thank you. This here is going to be what? I gotcha. It's negative. Good. It's a negative sign there. Good job. Thank you. I'm glad you're awake. Good, because we don't want to do all this work and then what happened, right? Okay, so when we do some of the algebra now, notice this. Let's get rid of some of these highlights. What's this? Is that gone? So if you want, let's do something like this first, though. How about if I just do this? I'm going to keep that there like this. Negative square root of x over 2 square root of x. Is that right? Minus. I'm going to distribute here my division here. So 1 over 2 square root of x minus the square root of x over 2 square root of x. Let me show you the details here. This is all over x. Okay, so all I did here was the following. Take that denominator and put it under here, both of those terms. You guys see that there? I'm distributing here algebraically this multiplication. All right, so I'm going to keep it that way. And then I'm going to say to you guys, let's do some more simplification here. Minus square root of x over 2 square root of x minus 1 over, let's get rid of the parentheses here. Minus 1 over 2 square root of x plus what? Square root of x over 2 square root of x. Everything over that x. And at this point, we can notice that, oh, cancels, right? So this is really going to be negative 1/2 minus 1 over 2 square root of x plus 1/2 over x. And you notice that this term and this term cancel. So we get that second derivative to be minus 2 square root of x divided by x. I'm going to write this as, see this division? I'm going to use the horizontal definition. And then at this point, we get minus 1 over 2 square root of x times the reciprocal, 1 over x. So my second derivative function will be minus 1 over 2x square root of x. So double check to see if we're okay with that. Okay, is that what we get for the second derivative? All right, you guys okay with that? Yes.
Can you go a little bit more?
Yeah,
It's fine.
check that. Okay, you guys okay with that one? Yeah, double check my arithmetic here. Now, we have to do with this sine analysis. So by sine analysis now, again, we have to find where this numerator equals 0. I'm going to bring the negative sign up there. So I say, oh, negative 1 is 0. This what? Never what? Happens. So that means my second derivative of the function is never 0. Okay. Never happens. But is that second derivative undefined, right? You have a rational function. The answer is yes. So you're going to take here the denominator, set that equal to 0 to find where that second derivative is going to be undefined, right? Or does not exist. 2x square root of x is 0. And this is actually 2x times x to the 1/2 is 0. 2x to the 3/2 is 0. Which means x to the 3/2 is actually 0. Or x is 0 to the 2 what? Thirds. You're solving this for x. And that means simply that x is 0. So this is useful information. Okay? So what we know is the second derivative is undefined. Does not exist, right? The rational function is undefined when x is 0. And what that means there is you don't have a second derivative at x is 0. So let's actually recall the domain here. Is 0 allowed in the domain? Do you guys remember? What's the domain of this function? Set of all x such that x is greater than or equal to 0. So I just want to point that out. So when we go and we finish our sine analysis, we just know at 0 for the second derivative function, the rational function was undefined. That creates region 1, region 2. However, we don't care about region 1 because our domain again is what? Greater than or equal to 0. So I just need a single test point. I can use 1 as a test point. And that's for the second derivative again. So you got to go back over here for the second derivative. And for an input value, we get to plug in what? 1 here. So what do you guys know about the sign here? Since I already have a negative sign, when x is 1, that denominator down here, right, is going to be 1 times the square root of 1, which is times 2. It's going to be negative 1/2. The point I'm making is region 2 is going to be what? Negative or positive? Negative. And what that means is the curve is concave what? Down. Does not hold water. There is no inflection point because of the fact that there's no location on the curve in which you change your concavity, right? You don't change concavity at all. So this is essentially all the analysis you guys need here. All right, so let you guys know, this is that analysis for you. So at this point, what do you guys think you're going to have to do now? What comes next after all this? We have to what? We have to sketch the what? We have to sketch the curve now. Okay, we're going to use all this information to sketch our curve. Now, I'm not sure if that graph paper will fit here because of the, just so you guys know, this, you know, on this iPad, there's a region here that starts the next page, and I can't remember if that works well. Let's see if it does. we need our graph paper. Okay. Yeah, so this thing is gonna, let's see if we could do this here. Yeah, I have to resize this again. So I'm gonna undo it. Let's add it again. Yeah, let's see. Come on, resize this thing. Yeah, see what I'm talking about? It doesn't like being on that boundary. So we'll do it right here. Okay, that's my point. It didn't like being on the boundary there in the middle. We're gonna have to sketch the curve here. All right, remember, what's the domain of the function? Right, it's all positive values. And go back over here, like I mentioned here, this is essentially a lot of good information here. Okay, that at 0, this is even though that's your first derivative, your curve is doing what? It's increasing at 0 here to, from 0 to 1, you got increasing. Is that right? And you're increasing to the value 1, I believe. This is the local max. So I'm going to use this concept, increasing on that interval to 1. So I'm going to start at 0, because isn't that where I have an intercept? My x and y intercept is at the origin. Can't remember. Is that true? Go back. Where are your intercepts? See that here? See these two locations? This is the y-intercept. Here's my x-intercepts, 0, 4. So let's plot those. Start with those intercepts. 0, and then 1, 2, 3, and 4. Good. What do I know is happening at, is it x is 1? Do you guys know? What's the value here for the increasing portion? That goes to what? Yeah, 0 to 1, and then my highest value here is 1, so it's kind of a, at 1, the highest value is 1, so you're going to be right there. Bless you. So we're here, here, and here. Is that right? Those are my two intercepts, x-intercepts, y-intercepts. The x-intercept is the same as the y-intercept. It's the origin. And then I'm going to say to you guys, increasing and what? Decreasing. Is that true? If you go back and you look at that sign analysis on the first derivative. Okay, we're looking at this picture right here. Let's get rid of all this colorization since it may be distracting. So we're looking right here. This is the hill we're looking at right here. Okay, we're going up and down at that location. And we're going down forever as x goes to what? Positive infinity. Remember this limit? We had as x goes to positive infinity, what's the end behavior going to be? X goes to positive infinity. Where does y go to? Negative infinity. So what that means here is my behavior is going how? I'm going to negative infinity forever. Is that true? Okay. Now, what about concavity? What does my concavity say? At 1, what do you guys notice happening at 1? Right? From 0, well, we didn't put the analysis. Good. Let's put the analysis. We just went straight to the sketch. F is what? Concave down only from what interval? 0 to infinity. So it doesn't hold water. So if you say, how does that look to not hold water? Well, it looks exactly like this. Just make sure you draw a curve, not straight lines that don't hold what? That does not hold water. So that's essentially how the curve looks. And of course, this goes on forever. So I can get rid of my straight lines. Okay, you guys okay with that? And I have all the important details here. This is at 1. This is 0 at 4, and this is at 0. So we have all the details. We went through all the analysis. Now, let's make sure this is correct. So we're going to put y equals 2 square root of x minus what? X. And what do you guys see here? Let's make it bigger here. Okay, you guys notice this point again here? See if it doesn't give us, I think it only gives us what? Yeah, it gives us these points if you can see it here. Okay, if I touch it, you guys could barely see it in gray. It gives you the x-intercepts and the y-intercept and that largest value at 1, 1, 1 right in here. See that point? These are the points that it's going to give us. Boy. Yeah, we lost those points. Anyway. Yeah, at these locations. See that 1, 1, 0, 0, 4, 0. And that's how the analysis works. So it looks like we're pretty good here. Okay, good. Should we try another one? Should we try another? Let's take a look here. How about sine minus tangent? Let's give you guys a quick break and we'll come back and try this one, okay? That way I can save some of this too, just in case. All right, let's try one more of these here. We're going to go over the curve sketching guidelines again. So the first thing is going to be define the what? What's the domain here? So we're going to notice that they did not restrict our domain. Remember that the domain is essentially where it's all real numbers except for where this function may not be what? Defined. Is that right? So let's recall something about tangent. What's tangent? Sine over what? Cosine. So right off the bat, we know we have some restrictions here for the domain. Is that true? Okay. The domain here, we're going to have to consider where cosine is 0. Because those values we have to throw out. So cosine is 0 here. Do you guys remember, how do you actually look at that? Cosine is 0. They have no restriction here. So there's a lot of values, infinitely many values, where cosine is actually 0. So I want to consider, how does your cosine curve look? Okay, if you guys remember here, this goes a long way to say y equals, go with this function here, cosine. Now, there's a lot of values where cosine is 0. Is that right? Cosine is 0 at this location, if we could get there, yeah. Tell us what the points are. Pi over 2. What else? 3 pi. Is that right? Every time I resize this, it seems to go away. There we go. Pi over 2. 3 pi over 2. What's this going to be? 5 pi over 2. Is that right? And you're going to get 7 pi over 2. But also, it's going in the other direction too. So if you guys notice, that point will be negative pi over 2. And what? Negative 3 pi over 2. And by the way, cosine is symmetric, right? Cosine is actually even. Okay, so you guys notice that cosine's even. So when you go back over here, we know that x equals odd multiples of pi. All right, odd multiples. So we say 2n plus 1 pi over 2, where n is an integer. Okay? N being an integer means that n could be any one of these values. Negative 2, negative 1, 0, 1, 2, forever. So I want to just start off very simply to say to you guys that x could not be plus or minus 1 pi over 2 plus or minus what? 3 pi over 2 and so on. Okay? So we have to throw out those values because this is where cosine is not, cosine is 0 at those values and this function will not be defined. So your domain really, at the end of the day, is going to be set of all real numbers x such that x is not all the values that we just listed. Plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, and so on. So we have to consider that. Okay. And then we go to the next step, which is going to be our intercepts. So for the x-intercept, again, we let y be 0. And we solve for x. So that means over up here, we have 0 here. And this is the equation we get now. We get 0 is sine x minus tangent x. Or we can say 0 is sine x minus tangent is sine over what? Cosine. Is that true? Okay. So we're going to have to solve this trig equation here. Now, what you can do to solve this trig equation is we can subtract these rationals. We can think of it that way and say, okay, you got this over 1. And what that does for us is we have now sine x times cosine x over cosine x minus sine over what? Over cosine. And what this gives us is a way to actually solve this here. Sine cosine minus sine over what? Over cosine x is 0. Now you guys know, when is a fraction ever 0? Whenever the numerator is what? 0. So that implies that sine x cosine x minus sine x equals 0. Factor out your sine. And you now have cosine x minus 1 here. Okay, and so now we're going to use what's called the zero product rule, meaning I have one term multiplied to another term. And the product is what? 0. That means the following here, by the zero product rule. That means either sine was 0 or cosine x minus 1 is 0. Now, if I add 1 to both sides here, here's what this means. Cosine is 1 And so I have these two equations here. Okay, I got sine is 0, and I got cosine is 1. So I'm going to have to solve both of these here in general. And with that knowledge, we're going to have to remember the values for sine being 0. If you guys remember, where is sine 0? Do you guys know? That's when x is what? 0, pi, 2 pi, or simply when x is really n pi, again, n is a integer value. So this is the solution to this equation. What that means for us, let's consider, that means this x is going to be 0 plus or minus pi plus or minus 2 pi, and that goes on forever. Now, where is cosine 1 here? I might still have my cosine curve. Oh, there it is. So cosine is 1. Let's take a look at this. At this point and at that point. Is that true? So it's at 0 and what else? 2 pi. And in fact, since the period for cosine is 2 pi, we can keep adding what?
2 pi.
2 pi forever. So that'll be 4 pi. That's where it'll be 1. And similarly in the other direction, you can subtract. Yeah. So I want to point out to people that knowing those fundamental curves goes a long way. So that's an even multiple of pi. Is that right? So we can describe it this way as x equals even multiple. How do we write an even number? It's 2n pi, where n again is any integer. So this is what's called the general solution here, so you guys know. We're going to look at some of these values and say, okay, that means x is going to be, let's be careful here. Can n be 0? What's cosine of 0? N could be 0, is that right? Yeah. So we're going to say 0, what is plus or minus what? 2 pi plus or minus 4 pi. So double check, I think we're okay. And we've solved both of these equations. These are the locations of my what? These are the x-intercepts. So this is going to be a very interesting curve here. Now let's find the y-intercepts. Let's just label that x-intercepts here. So for your y-intercepts, let's remember here, the procedure will be to let what? X be 0. Solve for y. Now you already noticed it's already solved for y, right? Y equals sine x minus what? Tangent x. Is that true? So I'm going to let here my x value be 0 now. So this gives me y is sine 0 minus tangent of 0. Or we can say, since sine of 0 is 0, tangent 0 is also 0. So we actually have 0 minus 0, or y equals what? 0. So, you know, you have this y-intercept at the origin, and you have a bunch of these x-intercepts here. So you guys know. So that's a start to have to sketch this curve. Now the next part is going to be the symmetry part. So this is going to be very interesting for us. Since our function is what? Sine minus what? Tangent here. So for symmetry, let's use the definition again, right? It's going to be even, it's going to be odd, it's going to be neither, and we know it's periodic because these are trig functions, so it's going to be periodic. So let's think about this, right? We just have to replace the x with the negative x here. Okay, so you're going to plug in, wherever there's an x, you plug in a negative x. So let's see what that gives us. F of negative x is sine of negative x minus tangent of what? Negative x. So we know sine is even. Is that true? So that means, in this case here, f of negative x is going to be sine of what? Sine of x, because my sine curve is what? Even. Is that right? Now, we have here minus. Now, minus what? What do you guys know about tangent minus x? So now we're over here. We answered what this question was. What's this tangent of minus x? Anybody remember about tangent? Is tangent even or is tangent odd? Tangent was what? That was an odd function. Is that true? So what does that mean? We got minus tangent x. Is that right? Is that true? You guys okay with that? All right. Sine x plus what? Tangent x. Is that right? Now this is f of minus x. So, what do we know about this here? Here's our conclusion. F of x is not the same as f of minus x. How are they different? Can I erase all this here? You guys have that already in your notes, right?
One's negative, one's positive.
Yeah, this is where they're different, right in here. Let's see if we can. Negative and what? Positive. So that's enough to say that this is what? Even. I'm not even, sorry. This is not true. Now, is f of x equal to the opposite of what? F of minus x. Because what the opposite now is,
Sir?
yeah.
And one sine is, isn't sine odd?
Sine, oh, I'm sorry, sine even or odd?
Odd.
Sine is actually odd. That's right.
Oh.
Good job. Not even coffee helps. Okay. So let's still double check here. Is f of x not equal to f of minus x again? This is what? This is still a valid statement. Is that true? Okay, so that means it's not even. However, let's look at this statement now. We have to ask, is this function here, well, here's what it really is. Let's go back. They'll say, is f of minus x equal to minus what? F of x. So we already know what f of minus x is. It's right here. Is that right? So let's find what minus f of x is. So this is minus f of x. It'll be minus 1 times. The original function is sine what? Minus what? Tangent. Is that right? So minus f of x is minus sine x plus what? Tangent x. So what did we just notice about this here? They're the same. So what we know here is that f of minus x is minus what? F of x, which means your function is actually what? Odd. Is that true? Double check. Yep, it looks like you guys are okay. You're right. Sine of minus x is minus sine x. It's actually odd. So this function is odd. Now, why is that important? What do you guys know about odd functions? What does it mean about their symmetry? They're symmetric about the what? The origin. So it's symmetric about this origin here. And if I were you, I would think this. If you say, what are some odd functions? I'm going to just remind you guys, x. My first odd function that you ever see is x. The next one will be x cubed and so on, x to the 5th power. So if you notice the odd functions, if I just look at x to the 3rd power here, this is what it means to be symmetric about your origin. You're really symmetric about two things. you're symmetric about the x-axis. Oops, let's undo that. You'll be symmetric about the x-axis and the what? Y-axis, to be symmetric about the origin. So if I reflect this curve about the x and y-axis, this is what you get. I take this curve here, this portion, reflect it about the what? The x-axis, and you say, okay, this is how it looks. Now reflect it about the what? Y-axis, and then if I do that, this is how it looks on the other side. So this is what we mean to be symmetric about the origin. Okay? Anyway, just want to let you guys know that this is an odd function. It'll be symmetric about our origin. So how does that help us, you guys think? Why is this an important detail? To know that this is symmetric about your origin, what do you think we want to do when we sketch the curve? We're going to note. We want to only consider, and this is only for your sketch, consider what? Since it's symmetric about your origin. Consider the positive values, and that's all to the right of what? 0. Because we could sketch to the left of 0 by this symmetry, being symmetric about our what? About our origin, if that makes any sense to you guys. Okay, just want to let you guys know that's going to be something we consider. Also, since these are trig functions, what do we know about symmetry? Since these are trig functions, this curve is what? This is periodic. We're going to have to figure out what is the period here, since they're periodic. So we're going to have to think about these kind of things here. Okay, and you can already see essentially for the x and y intercepts, or at least the x-intercepts, we can see some interesting sort of behavior here. Okay, so anyway, just point that out to you guys. And then let's go to the next kind of question here. What comes after the symmetry? Do you guys know? After symmetry, what do we think about? I think we have, what do we have here? Asymptotes? Right? So let's remember your curve is y equals sine minus tangent. Or we consider y equals sine minus tangent is sine over what? Over cosine. So going back to pre-calculus maybe, even though this technically is not a rational function, it's rational-like, you're going to have these what? What are you going to have here? Do you guys know what you're going to have? Where is cosine 0? Right? Cosine is 0 when x is what again? You already answered that question. What does x have to be? Plus or minus n pi over 2? Let's be careful. Isn't that where cosine is 0? Uh-oh, let's go back to the domain question. Maybe, where's the domain? Oh, sorry. It's right here. It's odd multiples of pi over 2. Is that right? Yeah. Okay. Now what that means here is x is going to be odd multiples plus or minus what? Pi over 2, plus or minus my 3 pi over 2, plus or minus 5 pi over what? 2. And that goes on forever. So here we go. So this is a location of what kind of things did we just find? Vertical what? These are my vertical asymptotes. Now, let's go to these questions here, horizontal asymptotes, right? This is my location of vertical asymptotes. So for the horizontal asymptotes, we're going to have to look at that limit as x goes to infinity now for sine minus what? Tangent. So if I look at this by definition of, or by a property, the limit of what? A difference is difference of limits. Okay, so I'm going to have to find these answers separately. Okay, because this is what we've been doing. We find that limit, and then we find the other limit, right? And then make sure we take the difference. Is that right? See how we've been doing that? So I want to look at the details here for this. So I want you guys to notice something here. This is going to be an important lesson. The limit as x goes to infinity for your sine curve. What is that going to be? Because yes, we can think of what again? And what? And behavior. So what do you guys think that limit's going to be here? You're going to have a problem here. Let me show you what I mean by that. This limit does not exist. Now, you might say, why does that limit does not exist? It's because your sine curve, ladies and gentlemen, oscillates between what? Plus or minus 1 forever. That's going to happen as what? As x gets big. That's what happens for your sine curve. So, does not exist is not saying infinity or minus infinity here, at least in a calculus 1 sense, because you're going to take calculus 2, you're going to see what does not exist means there. But in terms of calculus 1, this isn't infinity or minus infinity. It's not even a finite value because as x gets big, since our function's periodic, if you look at this curve here to say, well, what does sine look like? Right? Where's our y? Y equals sine of x. This is what we're saying. This curve oscillates between plus or minus 1 forever as x gets big. So it doesn't go to infinity, right? It doesn't go to minus infinity. It doesn't go to a finite value. It oscillates forever. So because this oscillates forever, if you guys can see that, as x goes to the right forever, the same thing's happening on the other side as x goes to the left forever. Minus infinity, right? So this is a situation where we say it does not exist. And you're going to find a similar situation if we look at this curve now. Maybe we could put tangent there next to it. Y equals tangent curve now. You're going to find the same kind of thing.
They're intercepting.
Well, they are, but my point is, as x gets big forever, your y coordinate doesn't go to anything either. It's oscillating between what? Yeah, we're going to have some issues here, okay? So I want to say to you guys, this is kind of an example where they tell you that this limit does not exist. All right, so you have no horizontal asymptotes. And similarly, if you try to take the limit now of tangent as x gets big forever, you're going to have an issue kind of there too. So I just want to point that out. Limit of sine, let's see if we can factor. No, it doesn't help with refactor. So anyway, we'll take a look now at the next step. What's the next step after the asymptotes? Do you guys know what the next step is? Yes. Where is this going to increase or what? Decrease. So we know already sine analysis on the first derivative. So let's look at that derivative function here. Here's my function. My function is sine minus what? Tangent. So f prime x is going to be the derivative of sine, minus tangent. And again, derivative of a difference is difference of what? Derivatives. So, what's the derivative of sine again? Cosine. What's the derivative of tangent? Secant squared x. Is that right? Okay, you guys okay with that? Now remember, what you're going to have to do eventually is you're going to have to set this derivative equal to 0. Is that right? So what I'm going to say to you is I'm going to do some subtraction here. I'm going to simplify this, by the way, algebraically. Because here's what we know. That cosine minus secant squared by our properties, or I should say by our what? Identities, right? What's the definition of secant, really? Isn't that going to be, since this here, the secant squared, is the same as writing that to the second power. What's the reciprocal identity? Is that 1 over cosine? You guys okay with that? So we're going to have to solve this equation, and it's going to be very helpful if everything is in terms of what? Cosines. So take a look. This is the work we do. We use the reciprocal identity. And then now, I'm going to say to you guys, write it this way. Multiply your top and bottom by what? By that cosine. Bless you. So you end up now with, and it's actually not cosine, but cosine what? Cosine squared, yeah. Okay, so you end up with cosine cubed x over cosine squared minus 1 over what? Cosine squared. So my first derivative here is going to be cosine cubed minus 1 over cosine squared. All right, you guys okay with that? Now here's the first derivative function. So remember, this function here is rational like. It's not technically irrational. So when we do sine analysis, remember how this works. You have a rational like function. You set the numerator equal to what? 0. You're going to try to find where that first derivative equals 0. Since it's rational like, that means cosine x cubed minus 1 equals what? 0. Okay, you guys okay with that? And here you're going to have to solve for what? Solve for x. This is a trig equation. Anybody remember how you do that? Let me show you guys how you can do that, right? When you're going to let t here, here's one way to do this. You can solve this by factoring because you're going to let t be cosine. And if that's the case, you end up with t cubed minus 1 is 0. All right, so you can now give this to your younger brothers and sisters in beginning algebra because they have a difference of perfect cubes now. So this is going to be t minus 1, t squared plus t plus 1 equals what? 0. Now that means two things by using the zero product rule. That means t minus 1 is 0. That means t squared plus t plus 1 is 0, because whenever you multiply two terms and it equals 0, you use the zero product rule. Is that right? Okay. This means t is 1. We're going to use that. And the other one, if you guys notice, the t squared plus t plus 1 equals 0. Well, that's not factorable. This gives you what's called complex what? Solutions. It's not only not factorable, your solutions are complex or imaginary. So this is calculus of what? Real numbers, not complex numbers. So what that means for us is we get to throw this what? This portion out. And that just means that t here is 1. Well, what is t anyway? Cosine x. So what that means now is cosine of x is 1. Now, where does that happen? We already know. Where's cosine x 1? Well, that happens when x is going to be what again? All those values, right? I believe it's 0. What else? 2 plus or minus what? 2 pi. You guys remember this one here? Yeah. 0 plus or minus 2 pi plus or minus 4 pi and forever. So this is where my first derivative is 0, or I have horizontal what? Tangents. Okay, you guys okay with that one? And then we got some nice critical values. What about the denominator now? You say, well, what about my denominator equal to 0 here? Now I have to do the denominator. And you say, okay, my denominator here, cosine squared is 0. So let's find where the denominator equals 0, right? Where is this undefined? Or does not exist, right? This is a does not exist. Well, that's where your fraction is undefined. So your fraction's undefined where cosine squared equals 0. Now, I can do the t substitution again if you wanted. And you can say, okay, can I let t be cosine again? And you get t squared is 0. Well, what does that mean? T is 0. Or we can say what? Cosine equals what? 0. Now, where is cosine 0 going to be? Cosine 0 is where? That x is what? Plus or minus 2n plus 1 pi over 2. Is that true? Is it the odd multiples of pi, I believe? Plus or minus? So in this case, again, we can look at some of those values. Again, these are critical values. Are they? We'll see. X will be, what is that? Plus or minus 1 pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, and this goes on forever. So we're going to use these values and these values because this is where you have, again, what? Where that derivative is 0 or that derivative is what? Does not exist, so we don't know. So sine analysis. Now, let's simplify some of this here. Let's at least set this up. First derivative. Where is this derivative 0? At what? 0, 2 pi, what? 4 pi, minus 2 pi, minus 4 pi. This is where my derivative is what again? Do you guys know? That first derivative is 0. Is that true? We're going to try to set this up for you guys. What about the other? What do you guys notice? It's undefined where cosine squared is 0, right? So where's it undefined now? Yeah, so here, don't we have what? Pi over 2, 3 pi over 2, is that right? Pi over 2 and what? Is that 3 pi over 2? And that's undefined, is that true? And it's also on the other side. So it's going to be what? negative pi over 2, and what? Negative 3 pi over 2, is that right? So we're going to have to make some space here. So I might actually just do something like this personally. I might just look at what? This portion from what? This positive 2 pi, negative 2 pi. Okay. And I'll look at this in greater detail, and I'll do my sign analysis with this. So this is going to, help me in sketching the curve, because I'm going to find, if you guys remember, at these values here, we're going to have what? Vertical asymptotes, right? You guys okay with that? Anyway, we're out of time here, so we're going to have to finish this some other time. Either I'll do it at home, or we'll see about next time. But we're out of time with this one. But I wanted to go through a trig version as well. Let's go back and figure this out. Remember, we have vertical asymptotes. Is that true? So here's our vertical asymptotes. Again, this is kind of like we just got through discussing. Those are odd multiples of what? Pi over 2. Is that right? And they're plus or minus. So this is where our vertical asymptotes are. We know we don't have a horizontal asymptote. We went over that. That sign. This did not exist. This was periodic. So I'll talk a little bit about that. We're finding where the function increases, decreases. And we found where the derivative was 0. The derivative did not exist. We solved this portion here. Okay, remember here's what I want to remind you guys. This derivative did not exist because my denominator here was 0. Cosine squared is 0 here. Remember this? Well, this is where the derivative does not exist. This is the location of our what? Vertical what? Asymptotes. So we have that kind of issue there with our vertical asymptotes. Okay. So I want to take a closer look at our sign analysis here. So let's take a closer look here. And I'm going to make this a lot bigger now. And let's remember here, our function here, well, we'll write it down, but so I have 0 here in the center, and my derivative was 0 here. I also have, where else was that derivative 0? Yeah, all the way out here, maybe to what? 2 pi, right? Here's 0. That's the first derivative. And then the other one will be all the way out here at minus 2 pi. So I'm looking at a snapshot around the origin here. Okay, and then I want to remind people here, you have some other things happening here. Right, go back. Pi over 2, the first derivative is undefined because you have a vertical asymptote there. So you got pi over 2, and then you have what? 3 pi over 2. This is where that derivative was undefined. And then on the other side, don't forget, minus pi over 2, and then minus what? 3 pi over 2. And that's because you have vertical asymptotes. Okay? So remember this. This is what we just mentioned. And then we have to find a test point for every one of these regions, right? So this is going to be kind of interesting here. We're going to have to go through a little bit of detail here. Pi over 4 as a test point. And then to the right, we're going to use between pi over 2 and 3 pi over 2. Between 90 degrees and what? Could we use pi there? Okay. That's a good selection. And then on the other side, minus pi over 4 as a test point. And how about what over here? Minus pi. And then what about over here as a test point? What's between 270 and what? 360? We're probably going to need another what? You're going to use 5 pi over 4? What's 5 pi over 4? See, 1, 2, 3, 4. Okay, this has to be between 270. How about 7 pi over 4? And way over here, you're going to have what? Minus 7 pi over 4 here. These are all my test points here. And we're going to test the first derivative. And what was the first derivative again? Do you guys remember? How about this? What's our first derivative? Go back here. Yeah, first derivative is cosine. Well, it's going to be, let's use, here's my first derivative. Is that right? Cosine x minus secant squared x. So let's write it down. So here's what this is. Let's do it a little nice. Like told you guys, I can write on the board, but as soon as you write on this thing, it's really weird. Here we go. F prime x. What was that? Cosine x minus secant squared x. Okay, so we're going to test some points here. And then you might think that it would be easier maybe to write this as 1 over what? Cosine squared. We'll see. Let's plug in some values here. We got to test these regions. So I'm going to test here pi over 4. So I got to plug in pi over 4 here and here, wherever we want, right? So we got to plug in that pi over 4. So we're going to look at f prime of pi over 4 will be cosine of pi over 4 minus 1 over cosine what? Square root of pi over 4. Now, I could do the arithmetic. We just talked about this in great detail, but we're running out of time. So I'm going to try something here. I'm going to do this here. Okay? I'm going to try putting it here. We're going to have what? Cosine of pi divided by 4. Okay, is that right? Minus, and I'm going to find my secant curve here. Secant of what? Yeah, it'll be secant squared. So let's go back here and let's see if that works. And we'll put pi over 4 again. Pi divided by what? 4. What do you guys get?
Negative.
It's negative, is that right? So we're going to have a negative region there. Negative 1.2928. Okay. The point is, this is negative. So this region here is going to be negative. Remember that? We're going to partition here. And we're going to do the other side as well. So let's plug in now. Let's do the test point now of what? Pi. Is that right? So we could do pi. Plug that in. And maybe that one would be faster if we just say f prime of pi is cosine pi minus 1 over cosine squared of pi. Do you guys know what cosine pi is? What's cosine pi? It's negative 1. Is that true? So we know this portion here is negative 1. And this portion is negative 1 squared. Is that right? So I'm going to get negative 1 minus 1 over 1. Is that true? So what does that give me?
Negative.
That's going to be negative 2. Is that right? So it's negative. Okay, I got a negative here for this test point. Now let's test what? 7 pi over 4. Now I can do the arithmetic again here, but let's go to this, let's go over here. We're going to put what? 7 pi over 4? 7 for the sake of time. What do I get? What do I get now?
Negative.
Is that still negative? It's the same value. Okay, negative. So we know this region is going to be what? Negative. Is that true? All right. Now what about the other side here? So let's look at these curves. What about the other side? If you guys remember here. We know, are these functions even or odd? Did we talk about that? Do you guys remember if these are even or odd? It was an even function? Is that true? I think you're right. That's going to be even. Is that right? So if it's an even function, what do you think is going to happen? What does an even function mean? What about your symmetry? For symmetry, what do you guys know about even functions? Let's remember from the other day. I'm going to erase some of this stuff here. Let's get rid of this. So when you have an even function again, boy, let's get a super big eraser. Let's recall, is this even? Let's use some symmetry here. So my function f of x was cosine x minus 1 over cosine squared of x, right? So we're going to find out what is f of minus x going to be. It's cosine of minus x minus 1 over cosine squared of minus x. And cosine of minus x, what do we know? Isn't that cosine x? Minus 1 over, that's still cosine squared x. So this is f of minus x. So sure enough, f of x is f of minus x. The function is what? Even. Now, that means it's symmetric about the y-axis. So let's put that in red. It's symmetric about your y-axis. What does that mean then? On the left here, does that mean these are also decreasing? Okay, you guys okay with that? Because of the symmetry. Now, essentially you guys are looking at the curve here. Because this is first derivative sign analysis. What that means is decreasing, 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 decreasing. Is that true? So we can actually start to answer some questions here. Notice that your curve is not increasing anywhere. Is that true? Because you don't have a derivative, that's what? That's positive, right? There's no region here where you have positive derivatives. So we can conclude here, right? Let's draw our conclusions here, that f is decreasing on what intervals? Now you have to describe this as intervals. Let's get rid of some of this stuff. Now our eraser's too big. Let's see if we can see the intervals here. Okay. Remember, this interval here from 0 to what? To pi over 2. What else? Pi over 2 to 3 pi over 2. 3 pi over 2 to 2 pi. So if you want, we can say 0 to pi over 2, right? Union pi over 2 to what? 3 pi over 2? Okay, is that right? Union what? To 2 pi, and that goes on forever. So we can generalize this, but for our curve sketching, we're going to keep it that way. And don't forget the other side. What's the other side? See this other side here? Negative pi over 2 to 0, right? Negative 3 pi over 2, negative pi over 2, negative 2 pi to negative 3 pi over 2. So that's happening as well. So just giving the details. Negative 3 pi over 2. And then negative 3 pi over 2 to negative 2 pi. And that goes on forever. So we know this curve is going to be what? Decreasing on these intervals. So that's how you can answer that kind of question. And then I'm going to remark here that you can kind of already sketch this curve here. And remember, let's actually do that. Let's kind of get this curve in. If I can find that photo, we can kind of do that. Now, hopefully we can do some of these here. So I have, where do I have my asymptotes? You guys know? At pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. Is that true? So I'm going to have to be careful here. Let me do something as well. 0 to pi over 2. So what's pi over 2 approximately? Do you guys know? That's going to be 3 divided by 2. That's a little bit more than 1. So I'm going to have to fudge here. Pi over 2, is that right? And then we have a what? Let's do something like this. 3 pi over 2. We have it on the other side too. Just to give you guys an idea, this is going to be, let's put it down here, maybe negative pi over 2. And then I'm going to do another, maybe 1, 2, 3, 4. Okay, so we have a minus 3 pi over 2, just to give you guys an idea. These are my vertical asymptotes. So even though we didn't finish with the analysis yet, I wanted to give you an idea of what this curve looks like just by starting to do things now. I'm going to use this information that we're talking about here, these vertical asymptotes. And I'm also going to use some other information. What were the x-intercepts? Remember in the beginning we found x-intercepts here as well. So your x-intercepts happened, oh, here we go. See these x-intercepts? 0, pi, 2 pi, plus or minus, right? Okay, we're gonna plot those too. 0, pi, 2 pi, okay. So we have an intercept here. 0, where's pi here? Is it, yeah, it's in the middle here, right? 0 pi, and then 2 pi, it's going to be maybe over here, I guess. And then you have the other side in the middle and over here. So let's make sure we label this correctly here. This should be pi. This should be what? 2 pi. Double check. Because I want to point out the detail. This is essentially how your curve looks. What you guys see here is how everything looks. Everything is doing what? You're decreasing. Look at this portion in the middle here, right? You're decreasing, but you're going through the origin. So essentially for that first part, I'm going to draw these decreasing lines. I'm going to draw these decreasing what? Lines. These decreasing lines here. This is what I'm talking about. This is essentially what the curve looks like. Okay, and you say, how do I know? Because we're looking up here at the analysis, and we didn't answer this question, but we will. We know that this is where your function is what? Decreasing. We also know something about what? Are there any extreme values? Right? There's also no what? No local max or local mins. Why do we know there's no local max and local mins here? Yeah, because you don't change signs, right? It's strictly negative. Your signs don't change for your sign analysis on the first derivative. So there's no local max, no local mins. But this is the key picture here. So, you know, to tell people, this is really the key of your sketch. And it's starting to look like this. The only question we have now at this point would be, you know, what do we have to answer? What about what? The concavity. And for concavity, what do we need? We need what? Yeah, it's always sine analysis on your what? Second derivative. Let's see if we can bring everything back here. So we need sine analysis on that second derivative here. Okay? Now, for sake of time here, I'm going to show you something here. I'm going to go out of the order here. For sake of time, I'm going to say to you guys that that second derivative function, doing this work, you're going to find the second derivative to be minus sine x 1 plus 2 secant cube x. Right? This is going to be the second derivative. Now you might say, okay, y. Okay, let's do the y then. What's my first derivative? Cosine x minus, what was that? It was what? Secant squared x. So I'm going to have to differentiate. So the derivative of a difference will be difference of derivatives. Right? And then what's the derivative of cosine? Minus sine. And then over here, don't forget, we're going to use what here on the we have to use what chain rule, is that right? Because you have the power 2. So that's going to give us by chain rule 2 secant x times the derivative of what? Times the derivative of secant, is that right? Which is minus sine minus 2. What's the derivative of secant? Secant what? Tangent. So minus sine minus 2 secant squared tangent. That's your second derivative, although what I did here was I wrote tangent as what? Sine over cosine, right over here. So use your identity here for tangent. Tangent is sine over what? Yep. So we get minus sine. If I factor out minus sine now, I'll get 1 plus 2. What is that? Secant squared over cosine. And that's factoring out the minus sign, so I get minus sine 1 plus secant cube. Now you might say, how did you get the secant cube? Because cosine, and using your reciprocal identity, put secant on the top. Is that true? So now I have 3 of those secants. So, or the third power. So here's that second derivative. And this is where we'd have to use our what? Sine analysis. Now, using the sign analysis here, I can go to that kind of detail. Yes?
You left cosecant cube.
Cosecant cube?
Yeah.
Should be secant cube, right?
Cosecant cube.
Oh, there's a 2. That's right. We need the 2. You're right. Thank you. Thank you so much. 2. So we're going to have to do sign analysis on that now. And we're running out a little bit of time here. I have that conclusion. But let me show you here. I'm going to try to do this curve. What was this curve to begin with anyway? Do you guys remember? Let me show you what this curve looks like, since you already kind of know. What was that curve that we started with here?
Sine A minus tan A.
Yeah, let's get rid of that. Okay, it's going to be y equals
Sine
sine x
A minus tangent A.
minus
Tangent
tangent x. Okay, as you guys can see this here, just want to make sure. Take a look at that point, the origin. What is that? Pi. What are these? 2 pi, 3 pi, 4 pi, and so on, even to the left. Negative pi. These were my intercepts. Is that true? And then you had all these asymptotes. So I want to show you here, we were really looking at sort of this portion of this. And as you guys can see, we have some concave down. Well, first of all, to the left of 0 is concave up. Concave right, concave down is to the right. Concave up, concave down, so it's alternating your concavity. So I want to remark that this is the curve we're trying to sketch. So if I go back here and say to you, sign analysis, I can give you some of my conclusions here so you guys know, and I'll write this down here. So sign analysis. When I went through sign analysis, because we're running out of time, I want to say to you guys, first, the first derivative equals 0 for these values of x. Right? When I went through this, x is going to be here. 0 plus or minus pi plus or minus 2 pi, and so on. That's because you'll find this is where sine is actually 0. And you're going to find that this portion here is never 0. Okay, that portion there is never 0, the second portion. So when you set them equal to 0 as a product, by the 0 product rule, you won't get 0 there. But also, you have to be careful here. Let me show you guys where you be careful here. Remember what secant cube is? That's 1 over what? Cosine cube. See that portion? This tells you now where your second derivative here does not exist. Okay? Because you can't have this denominator equal to what?
0.
Equal to 0. So, and then you say, well, when does that happen? Well, when I did my work on this here, where does it not exist? That happens when x equals, you're back again to the odd multiples. Plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2. That goes on forever. So you're working with the tools we just talked about earlier today with some of these other topics here. So you're going to find that this is what you're going to start to do with your sign analysis on that second derivative. So you'll take a closer look here on this. And, okay, you say, where is it 0 on the second derivative? You got 0, you got pi, you got what? 2 pi, and maybe I have to spread that out a little bit just in case. Minus pi, minus 2 pi, and then where does it, and this is where that second derivative will be 0. And then where is it undefined? Right? Pi, plus or minus pi over 2. Pi over 2 minus pi over 2. It'll be what here? Undefined at these two. And where else? 3 pi over 2. So you get 3 pi over 2 and what? Minus 3 pi over 2. You get undefined here. The point is you have all these regions. And when you go through this, here's what you guys are going to find with your various test points. I get here. 0, let me see if I could read this. 0 to pi over 2 is negative, positive, negative. And on the other side, we get positive, positive, negative, what? Positive, negative. So here's how we have our concavity here. So if we answer the question of concave up, right? Let's do our conclusion at least. F is concave up. If we can read this, just to at least give these answers, positive, positive. This one over here will be positive, by the way. Positive. So we can kind of write this up as concave up. Well, let's do it this way. Let's start with the positive intervals here. Pi over 2 to what? Pi union 3 pi over 2 to 2 pi union. This goes on forever, but we also want to include what? We want to join the left side there. We got negative pi over 2 up to 0, and we get negative 3 pi over 2 up to negative pi, and that goes on forever. So here's where we're concave up. If you want to say, what about concave down? This region, this region, this region, this region. So we can say again, F is concave down here. And the green regions, we're now going to say what? 0. Yeah, 0 to pi over 2. Union pi 3 pi over 2, and that'll go on forever. The negative, join it with the negative side there. Negative pi to negative pi over 2 union negative 2 pi to negative 3 pi over 2. And that goes on forever. So concave up, concave down, you guys already know what that kind of means. What does concave up mean? You hold water. You what? Don't hold water. Hold water. Don't hold water. Hold water. Don't hold water. Hold water. Don't hold water. What's the very last thing we want to talk about? The very last thing we have to look for. Do you guys know? Look for your inflection points. That's where you change concavity. But it has to be a point on the curve. Okay? It has to be a point on the curve. So, do you have an inflection point? Where? At 0? What about pi over 2? Nope. Where else? Pi. Where else? In this picture, negative pi. And you will probably find at 2 pi and what? Negative 2 pi, okay? So you're going to have these inflection points at those locations just by looking at where you change what? Concavity. So let's just write this down so we can get out of here. I know we're out of time. So inflection points are going to be has to be a point on the curve. 0, f of 0. Pi, what else? F of pi. We're out of time, right? 2 pi. F of 2 pi. Also, negative pi. F of negative pi. Negative 2 pi. F of negative 2 pi. And this list goes on forever. So we didn't actually finish. These are where our inflection points are. They're on this, labeled on this graph with sign analysis on the second derivative. You know, and that's kind of how you'd have to go through some of this curve sketching with this particular curve. So, and again, go back here and say, well, you can verify all the concavity in that picture, but there's a lot of tedious detail here for this one. Okay, so this is a long question to do, and anyway.